In a universe filled with countless wonders and mysteries, our understanding of the cosmos continues to expand in ways that were once beyond imagination. Scientists estimate that there are over 100 billion planets scattered throughout our galaxy alone, each one orbiting distant stars far beyond our own solar system. Many of these exoplanets, planets that exist outside the kinds of our solar system, are so extraordinary that they defy conventional understanding. From blistering hot atmospheres to intense and unrelenting storms, these distant worlds exist in extremes beyond anything we experience on Earth. Together, let us embark on an incredible journey to explore the fascinating atmospheres and climates of some of the most hostile and mysterious exoplanets known to us. When we think of planets, our minds often gravitate towards those that orbit our sun, the 8 familiar worlds that make up our solar system. However, there is an entire realm of planets that exist beyond our celestial neighborhood known as exoplanets. These planets are not bound to our sun, but instead orbit other stars in the vast expanse of space. The primary feature that distinguishes an exoplanet from other celestial bodies is its orbit around a star. Not just any star, but one that exerts enough gravitational force to keep the planet in a stable orbit over the course of millions or even billions of years. The diversity of exoplanets is staggering. Some are smaller than Earth, categorized as super-Earths, while others are massive gas giants that far surpass Jupiter in size. In order for a planet to be classified as an exoplanet, it must be large enough to not be considered a star. This means that an exoplanet does not undergo nuclear fusion within its core, a process that defines stars. Instead, these planets are made up of solid or gaseous materials, distinguishing them from the stars they orbit. Another key criterion for classifying a celestial body as an exoplanet is that it must not be a remnant of a star, such as a brown dwarf. These are objects that failed to become full-fledged stars, but still have some characteristics of them. To maintain its status as a planet, an exoplanet must actively engage in gravitational interactions with its star, which can also pull in other celestial bodies, resulting in planetary systems with multiple planets orbiting a single star. The methods by which astronomers detect these distant worlds are as sophisticated as they are diverse. 2 primary techniques are widely used to identify exoplanets: the transit method and the radial velocity method. The transit method involves monitoring the brightness of a star over time. When a planet passes in front of its star, it blocks a small fraction of the star's light, creating a brief but measurable dimming effect. This allows scientists to detect the presence of the planet, and by measuring the dimming's duration and frequency, they can gain important details about the planet's size, orbit, and atmospheric conditions. The radial velocity method, on the other hand, involves detecting the subtle gravitational tug that a planet exerts on its parent star. As a planet orbits its star, it causes the star to wobble slightly in response to the gravitational forces at play. This wobble can be detected by observing minute shifts in the star's light spectrum, revealing the planet's presence without directly observing it. Together, these methods have opened a window into the diverse and often extreme environments that exist beyond our solar system. Since the first confirmed exoplanet discovery in the 1990s, astronomers have identified over 5,000 exoplanets, each one representing a unique corner of our universe. As technology improves and new space missions are launched, this number continues to grow, offering fresh opportunities to study planets that may harbor conditions suitable for life. With next-generation telescopes and advanced detection techniques, scientists are refining their ability to uncover these distant worlds and learn more about the environments that shape them. The study of exoplanets raises profound questions not only about the nature of these distant worlds, but also about our own place in the cosmos. Do other planets harbor life? What are the conditions necessary for life to arise? Can Earth-like planets be found, and what might they look like? The ongoing exploration of exoplanets pushes the boundaries of our understanding and, in the process, challenges our view of life in the universe. Exoplanets are classified into several categories based on their physical and chemical properties. One of the most fundamental factors in classifying a planet is its composition. Gas giants, for example, are primarily composed of hydrogen and helium. These massive planets lack a solid surface and instead consist of thick atmospheres that can extend hundreds or even thousands of miles into space. Some of the largest exoplanets discovered to date are gas giants, much larger and more massive than Jupiter, the largest planet in our solar system. In contrast, rocky planets are made up of solid materials such as silicates and metals, and they possess a terrestrial surface that supports landforms like mountains and valleys. These planets are smaller and less massive than gas giants, with a structure that allows for solid land masses, making them potential candidates for supporting life. The difference in size and composition between these types of planets has profound implications for their evolutionary paths and also for their potential to support life. Ice giants such as Uranus and Neptune in our solar system offer yet another intriguing category of exoplanet. These planets have compositions that include significant amounts of water, ammonia, and methane in the form of ice, with temperatures much colder than those of gas giants. The unique characteristics of ice giants, including their frigid temperatures and volatile compounds, set them apart from both gas giants and rocky planets. The study of these distant worlds is vital for understanding the full spectrum of exoplanetary environments and the conditions that govern their formation and evolution. In summary, the discovery and study of exoplanets continue to captivate the scientific community and the public alike. These distant worlds, often existing in extreme environments, reveal the immense diversity of planets that populate our galaxy. With each new discovery, we come closer to answering fundamental questions about the nature of life, the formation of planetary systems, and our place in the vast, uncharted expanse of the universe. In the vast expanse of the universe, the environment in which an exoplanet resides plays a pivotal role in determining its classification. Among the many factors that contribute to this categorization, one of the most influential is the planet's distance from its host star. The proximity of a planet to its star can dramatically shape its composition and the physical conditions it endures. Planets positioned closer to their stars often experience intense heat, causing lighter elements to vaporize and escape into space. On the other hand, those residing farther from their stars, in the cooler outer regions, have the potential to accumulate gases and even form icy compounds. These environmental differences help form the intricate puzzle of planetary diversity that astronomers continue to unravel. But the importance of distance goes far beyond just the physical makeup of these distant worlds. It has a direct impact on the challenges we face when attempting to study exoplanets from Earth. The farther a planet is from our solar system, the fainter it appears in our telescopes, making it increasingly difficult to observe and analyze. Even with the most advanced instruments, capturing the light emitted by these distant worlds requires immense effort. As the distance between Earth and an exoplanet grows, so does the difficulty of gathering sufficient light to study crucial characteristics such as the planet's size, atmosphere, and orbit. One of the primary methods used to detect exoplanets is the transit method, which involves monitoring the dimming of a star's light as a planet passes in front of it. This technique is most effective when the star is relatively nearby, as the intensity of light from closer stars is far greater. This allows astronomers to more accurately measure the subtle changes in brightness caused by the planet's transit. However, applying this method to distant stars presents a significant challenge. As the light from more distant stars becomes fainter, the planetary transit signals can become increasingly difficult to detect, potentially causing valuable discoveries to go unnoticed. Similarly, the radial velocity method, which detects the gravitational pull a planet exerts on its star, is also affected by distance. Planets in close proximity to their stars tend to produce more noticeable shifts in the star's light due to the gravitational wobble caused by the planet's orbit. For distant stars, these shifts are much more subtle, making it harder to identify and confirm the presence of exoplanets. As a result, exploring star systems within a certain range becomes crucial for increasing the likelihood of detecting exoplanets, leading to more successful discoveries. Ultimately, the distance of an exoplanet from Earth influences virtually every aspect of our approach to studying these distant worlds. It determines the stars we can realistically observe, affects the methods we employ to detect exoplanets, and plays a key role in how deeply we can study their properties. Despite these challenges, astronomers continue to push the boundaries of what is possible. With the advent of innovative techniques and the development of increasingly powerful telescopes, scientists are steadily bridging the vast distance between Earth and the outer reaches of our galaxy. Each new discovery, no matter how distant, brings us closer to understanding the true nature of planets and our place in the cosmos. As we explore the many exoplanets scattered across the stars, each discovery adds a unique piece to the ever-expanding puzzle of the universe. For instance, one of the most significant breakthroughs in recent years has been the discovery of the TRAPPIST-1 star system, located in the constellation Aquarius. This system is home to 7 Earth-sized planets, 3 of which reside within the habitable zone, the region where conditions may be right for liquid water to exist. The discovery of TRAPPIST-1 has sparked a renewed interest in the search for extraterrestrial life, making it a landmark moment in the field of astronomy. Another groundbreaking discovery was the Kepler-186 system, located in the constellation Cygnus. This star system is home to Kepler-186f, the first Earth-sized exoplanet discovered in the habitable zone of a star similar to our Sun. This finding has profound implications for our understanding of potentially habitable worlds and serves to broaden our view of the diversity of planetary systems that exist in the universe. The discovery of such planets raises important questions about their atmospheres and whether they could support life to Earth, driving further research into the potential habitability of distant worlds. Similarly, the LHS 1140 star system in the constellation Cetus has garnered significant attention due to the rocky exoplanets it hosts. LHS 1140b, in particular, has attracted interest for its potential for atmospheric studies. Orbiting a relatively nearby star, LHS 1140b is accessible for detailed observation, offering a unique opportunity to learn more about its atmosphere and the conditions that may prevail there. Studying these exoplanets is essential for furthering our understanding of planetary formation and evolution, and helps us assess how rare or common Earth-like conditions might be in the broader universe. Each of these star systems not only serves as a celestial landmark, but also provides valuable insights into the processes of planetary formation and the potential for life beyond Earth. Their study is helping to reshape our understanding of the cosmos and our place within it, highlighting the importance of continued exploration. These discoveries are reshaping the narrative of our universe and redefining the possibilities for life beyond our own planet. Space telescopes have played a transformative role in revolutionizing our understanding of the universe, particularly in the realm of exoplanet discovery. Unlike ground-based telescopes, which are affected by the Earth's atmospheric distortion, space telescopes operate above the interference of the atmosphere. This unique vantage point allows them to capture clearer images and more precise data, making it possible to detect the faint light emitted by distant stars and observe the small changes that occur when a planet passes in front of its star. One of the most notable space telescopes in the search for exoplanets is the Kepler Space Telescope, launched in 2009. Kepler was specifically designed to search for Earth-sized planets in the habitable zones of stars, regions where conditions might support liquid water. During its mission, Kepler confirmed the existence of over 2,300 exoplanets, spanning a range of planetary types, from gas giants to rocky planets. The wealth of data provided by Kepler has been instrumental in advancing our understanding of planetary formation and distribution throughout the galaxy. Another key player in the exploration of exoplanets is the Transiting Exoplanets Survey Satellite, TSS, which was launched in 2018. Unlike Kepler, which focused on a single patch of the sky, TESS surveys a broader range of stars, focusing on those that are closer to Earth. This proximity allows TESS to detect smaller planets orbiting nearby stars, making follow-up studies more feasible. To date, TESS has identified thousands of potential exoplanets, many of which are now being studied in greater detail to learn more about their atmospheres and geological properties. Looking ahead, the James Webb Space Telescope, which launched in late 2021, holds even greater potential for studying exoplanets in detail. Equipped with advanced instruments, Webb is capable of analyzing the atmospheres of exoplanets, searching for chemical signatures of life, such as water vapor, methane, and carbon dioxide. With this new tool in the astronomer's toolkit, we are closer than ever to answering one of humanity's most profound questions. Are we alone in the universe? The discovery of exoplanets has opened up a vast, uncharted realm of atmospheric diversity. Each planet, with its unique characteristics and conditions, adds a new layer of complexity to our understanding of planetary systems. For example, some exoplanets, such as the hot Jupiters, exhibit thick atmospheres composed of elements like sodium and potassium due to their close proximity to their host stars. These gas giants endure extreme temperatures, often reaching thousands of degrees, an environment vastly different from Earth's temperate climate. Conversely, smaller, rocky exoplanets located within the habitable zone tend to have different atmospheric compositions. For example, Proxima Centauri b, a planet that orbits our nearest stellar neighbor, may possess an atmosphere capable of trapping heat, but it could also be vulnerable to intense stellar winds that strip away volatile compounds. These differences highlight the vast range of environmental conditions that exist across the universe. Another intriguing category of exoplanets is the sub-Neptunes, which are characterized by thick atmospheres dominated by hydrogen and helium. These mini gas giants often have upper atmospheres shrouded in clouds that periodically release heavier elements. This phenomenon is starkly different from Earth's atmosphere, which maintains a clear division of elements necessary for life processes. Studying these exoplanets provides us with invaluable insights into the diversity of atmospheric phenomena that exist in the universe. As astronomers continue to explore these alien worlds, each discovery brings us closer to understanding the conditions that might support life. The detection of certain gases, such as oxygen and methane, in an exoplanet's atmosphere is particularly exciting because, on Earth, these gases are produced by living organisms. When detected together on a distant world, they could suggest the presence of biological processes or the potential for life. However, the presence of gases like carbon dioxide, ammonia, or sulfur dioxide can indicate a more hostile environment. High concentrations of such gases can lead to extreme climates, such as a runaway greenhouse effect like that of Venus, where temperatures soar to levels inhospitable to life. These atmospheric signals serve as important clues, guiding scientists toward planets that might be capable of supporting life, or those that are too extreme for life as we know it to thrive. The study of exoplanetary atmospheres is thus a crucial frontier in the search for life beyond Earth. Each discovery, no matter how distant, deepens our understanding of the forces that shape planets and their potential for habitability. As we continue to explore these far-flung worlds, we unlock the secrets of our universe, inching ever closer to answering one of humanity's greatest questions: what lies beyond our own planet? And could we one day find life in the stars? Understanding the delicate balance and ratios of gases in the atmospheres of distant planets is more than just a matter of chemical composition. It offers tantalizing clues to a planet's geological activity, past, and potential for supporting life. For instance, the presence of volcanic gases in an exoplanet's atmosphere could indicate dynamic geological processes, suggesting that the planet's surface may be actively reshaping itself over time. This ongoing activity, in turn, could be crucial for recycling the necessary nutrients that support life. Such an interplay between the atmosphere and geology could dramatically affect whether a planet remains habitable, sustaining life, or conversely, gradually erasing its potential for habitability. By analyzing the atmospheric compositions of these distant worlds, scientists gain invaluable insights into their environments. Modern research techniques, including spectroscopic analysis, allow astronomers to study the light that passes through the atmospheres of exoplanets. This light carries with it the chemical fingerprints of the gases present in those atmospheres, revealing the building blocks of distant worlds. With the advent of more sophisticated technology, scientists are now more equipped than ever before to investigate these far-off realms, moving us closer to answering one of humanity's most profound questions: could life thrive beyond Earth? Wind patterns on exoplanets, too, hold significant promise for understanding planetary climates and atmospheric behaviors. Much like Earth's own weather systems, the winds on distant planets are shaped by a complex array of factors. including a planet's proximity to its star, its surface composition, and the internal temperature gradients that drive atmospheric movements. By carefully studying these wind patterns, researchers can start to unravel the atmospheric complexities of exoplanets and gain a more nuanced understanding of how these elements interact. On planets that orbit very close to their stars, wind patterns can be especially extreme. In some cases, scientists observe a phenomenon known as superrotation, where winds move much faster than the planet itself rotates. This phenomenon can create drastic temperature differences between the day and night sides of the planet, contributing to intense weather systems that might be entirely alien to anything we experience on Earth. Such extreme wind patterns might even hint at the presence of dynamic weather systems, such as storms, that could reshape the planet's surface or influence its habitability. In addition to understanding the nature of the winds themselves, scientists can also infer crucial details about potential cloud formations and precipitation patterns. Wind currents that carry moisture across the surface might suggest areas of potential rainfall, while strong gusts could indicate the presence of storms. Through these atmospheric clues, researchers can form a much more detailed picture of an exoplanet's climate, how it changes with the seasons, how it might support life, and how different it may be from Earth's own weather systems. Grasping the full scope of wind patterns, including their temperature-driven dynamics and their ability to shape weather systems, is essential for constructing accurate climate models. These models are not only useful for understanding the conditions on distant planets, but also for making direct comparisons to Earth, thus enhancing our broader understanding of planetary science. By analyzing these distant worlds through the lens of their atmospheric winds, scientists are piecing together a more complex and diverse picture of the universe, where the possibility of life is always at the forefront of discovery. Exoplanets, planets located outside our solar system, have long captured the imagination of scientists and stargazers alike. These distant worlds, each with its own unique combination of temperature, atmospheric conditions, and surface composition, present vast opportunities for scientific exploration. Some exoplanets are located so close to their stars that their surfaces reach scorching temperatures, so hot that metals could melt, while others lie far out in the colder reaches of their star systems, perpetually frozen and inhospitable. Understanding the wide range of conditions that these planets can exhibit challenges traditional theories and forces scientists to rethink what it takes for a planet to support life. One of the key tools in understanding an exoplanet's surface conditions is the transit method of observation. During a planet's transit across the face of its star, light from the star passes through the planet's atmosphere. This light, absorbed and refracted by gases and particles in the atmosphere, provides scientists with a snapshot of its chemical composition. By studying these spectral patterns, researchers can infer critical details about a planet's temperature, pressure, and even potential weather conditions. The detection of water vapor, for example, could indicate the possibility of liquid water on the planet's surface, a key ingredient for life as we know it. Such atmospheric analysis has been performed on countless exoplanets, helping refine our understanding of what these distant worlds may be like. In addition to this, sophisticated computer models are used to simulate how different types of exoplanets interact with their stars. These models account for factors like the planet's size, mass, and distance from its star, helping scientists predict the likely surface conditions of a planet based on well-established physical principles. The surface characteristics of rocky planets, for example, differ significantly from those of gas giants, and predictive modeling allows researchers to narrow down the search for exoplanets with Earth-like qualities. As technology continues to improve, our ability to explore and understand these distant worlds grows exponentially. The James Webb Space Telescope, for instance, promises to offer unprecedented details about the atmospheres and surface conditions of exoplanets by observing them in a variety of wavelengths. Each new discovery is like a puzzle piece that brings us closer to understanding the fundamental nature of the universe and our place within it. As our knowledge deepens, so does our appreciation for the diverse environments that exist across the cosmos, expanding our understanding of the potential for life beyond Earth. Temperature fluctuations on exoplanets add yet another layer of complexity to our understanding of distant worlds. While Earth's climate is regulated by the gentle balance of its distance from the sun and the protective effects of its atmosphere, exoplanets exhibit an extraordinary variety of thermal behaviors. This diversity is driven by factors such as a planet's orbit, its atmosphere, and the amount of radiation it receives from its host star. These temperature variations push the boundaries of our existing climate models, forcing scientists to reconsider what is possible for planetary climates beyond Earth. Some exoplanets, for instance, experience extreme temperatures due to their close orbits around their stars. On such planets, the temperature can soar during the day and plummet dramatically at night. These sharp temperature swings can lead to volatile weather patterns that are vastly different from anything seen on Earth. In stark contrast, other exoplanets reside in more temperate zones where the temperature fluctuations are less extreme. On these planets, scientists have found evidence of consistent climates, potentially more Earth-like, driven by unique atmospheric compositions that trap heat in ways that could allow for stable surface conditions. For gas giants like the hot Jupiters, which orbit incredibly close to their stars, surface temperatures can reach levels that far exceed the hottest days on Earth. These blistering environments can lead to violent winds and unpredictable cloud formations, phenomena that are entirely alien to our planet. Even so, these extreme conditions serve as valuable case studies in planetary science, expanding our knowledge of what is possible across the universe. Ultimately, the study of exoplanetary climates, temperatures, winds, and atmospheres pushes the boundaries of our understanding, not just of distant worlds, but of the conditions required for life to thrive. These findings remind us that in the vastness of space, life may exist in forms that we have yet to imagine, thriving in environments completely unlike those of Earth. Each new discovery adds a new layer to the ongoing quest to find out whether we are truly alone in the cosmos. However, understanding the impact of temperature variations on a planet's potential habitability is an intricate and delicate balancing act. Scientists are tasked with deciphering how energy emitted by a star interacts with a planet's atmosphere, with subtle shifts in this interaction potentially altering the conditions for life itself. The complexity of this relationship prompts researchers to refine their models continually, incorporating new variables like planetary rotation, axial tilt, atmospheric pressure, and the presence of specific gases. These variables shape not only the temperatures on a planet's surface, but also the atmospheric dynamics, which can drastically alter a planet's climate over time. This is a dynamic area of study, one that evolves with every new discovery and breakthrough in astronomical observation. As we peer deeper into the cosmos, we find ourselves uncovering new insights into how planets evolve, how they are shaped by their environments, and how extreme temperatures can push their climates beyond the threshold of sustainability. The study of exoplanets, the world's orbiting stars beyond our solar system, forces us to rethink everything we know about climate and habitability. With each new discovery, we are reminded of the complex dance between physics and chemistry that governs the climates of alien worlds. It compels us to expand our understanding of life, pushing us to ponder what might be possible in regions of the universe we have yet to even imagine. When we turn our attention to exoplanets, these fascinating distant worlds, we are confronted with an array of geological features that challenge our traditional understanding of planetary formation. Scientists, using sophisticated tools to observe these far-off planets, speculate about the landscapes that could define these alien worlds. Some exoplanets may host towering mountain ranges, expansive plains, and deep canyons, geological features remarkably similar to those we see on Earth. Yet, the processes that give rise to these landscapes may differ profoundly due to the unique atmospheric conditions and chemical compositions of these distant planets. For instance, super-Earths, rocky planets that are larger than Earth, but smaller than gas giants like Neptune, may exhibit rugged terrains shaped by tectonic forces, much like the mighty Himalayas. However, the geological processes on these planets could be more extreme. Super-Earths may experience far more intense volcanic activity, resulting in vast plains of solidified lava that stretch across their surfaces, creating landscapes that are strikingly different from our own. In addition to the super-Earths, we must also consider the gas giants, such as Jupiter and Saturn in our own solar system. These colossal planets are largely composed of gas and have no solid surface to speak of. Instead of mountains and canyons, their geology manifests itself in the form of vast swirling cloud formations and powerful high-speed winds that define their atmospheres. In these planets, traditional geological processes, such as plate tectonics or erosion, are impossible as we understand them. What we do find are remarkable phenomena like massive, long-lived storms, such as the Great Red Spot on Jupiter, a storm that has raged for centuries, larger than Earth itself. For these gas giants, their dynamic atmospheres present a completely different set of challenges for scientists attempting to understand their nature and their potential to support life. Water, or the lack thereof, plays a central role in shaping the surface and atmospheric conditions of exoplanets. Some planets may harbor vast oceans that slowly reshape their surfaces through erosion and sediment deposition, just as Earth's oceans have done for billions of years. Other planets, however, might lack liquid water altogether, resulting in entirely different erosive forces. In these waterless environments, wind and dust storms could dominate, sculpting the planet's surface in a completely alien manner. This diversity of geological environments, from oceans to barren deserts, from volcanic plains to cloud-filled skies, provides endless opportunities for researchers to deepen our understanding of planetary science. But it also sparks our imagination as we wonder about the diverse possibilities that lie ahead in the exploration of the universe. A planet's distance from its host star is a fundamental factor influencing both its temperature and its potential for sustaining life. The closer a planet is to its star, the more intense the radiation it receives. This energy can raise a planet's surface temperature to levels that may render it uninhabitable, boiling away any water and transforming the surface into a desolate, dry wasteland. A prime example of this can be found in hot Jupiters, giant planets that orbit extremely close to their stars. These planets endure scorching temperatures, making them inhospitable environments for life as we know it. On the other end of the spectrum, planets that lie far from their stars experience freezing temperatures, which can cause any water present on the surface to freeze solid. Such cold conditions render these planets similarly inhospitable, as life would be unable to thrive in such frigid environments. The delicate balance between temperature extremes brings us to the concept of the habitable zone, the region around a star where conditions are just right for liquid water to exist. It is within this zone that the chances for life as we know it are highest. However, the habitable zone is not a guarantee of life. The composition and thickness of a planet's atmosphere play a crucial role in determining whether a planet can sustain liquid water. A planet may orbit comfortably within the habitable zone, but if its atmosphere is too thin, it may not be able to retain heat effectively. This could lead to extreme temperature fluctuations, making the planet too volatile to support life. Conversely, a planet with a thick, stable atmosphere could retain heat and create a more consistent environment, even if it lies slightly outside the typical habitable zone. Recent discoveries have shown that many exoplanets lie within their stars' habitable zones, raising the tantalizing possibility that these planets could harbor life. These findings offer a glimpse into a future where we explore not just the planets of our own solar system, but also the myriad worlds scattered across the galaxy, each with unique characteristics that could foster life or potentially host life forms completely different from what we have ever imagined. This exploration invites us to reconsider the very definition of habitability and life itself. The type of star a planet orbits is another crucial factor that shapes its environmental conditions. Stars come in a variety of sizes, temperatures, brightnesses, and lifespans, and these characteristics deeply influence the climate and potential for life on orbiting planets. Our Sun, for example, is a relatively stable, medium-sized star that has provided the right conditions for life to develop on Earth. Larger stars, however, burn much hotter and faster, emitting intense radiation that can strip away a planet's atmosphere. This creates harsh, inhospitable conditions for any potential life forms. Red dwarfs, which are the most common type of star in the universe, are cooler and dimmer than our sun. Despite their low temperature, red dwarfs have incredibly long lifespans, sometimes lasting trillions of years. Planets that orbit close to red dwarfs often experience tidal locking, meaning one side of the planet is perpetually facing the star while the other side remains in constant darkness. This creates stark temperature differences that challenge the potential for life. On the other side of the spectrum are massive blue stars. These stars are hot, bright, and relatively short-lived, often burning out in just a few million years. While planets within the habitable zone of blue stars might experience harsh conditions due to intense radiation and stellar winds, these stars also play a key role in the formation of new elements. As they burn through their fuel, blue stars create and distribute heavy elements into the surrounding space, providing the building blocks for future stars, planets, and possibly life itself. Despite the inhospitable nature of the environments they create, these stars contribute significantly to the overall evolution of galaxies, playing an essential role in shaping the cosmos. Each type of star, each exoplanet, offers a new chapter in our ongoing quest to understand the vast complexity of the universe and its potential for life, possibly even life that exists in forms we have yet to conceive. As we explore further, our imagination is bound only by the limits of our curiosity. Stars, in their life cycle, offer a profound window into the fate of the cosmos and the intricate interplay between these celestial giants and the planets that orbit them. As a star ages, its transformation from a stable main sequence star to a red giant is more than a simple physical change. It has vast implications for the planets within its reach. When a star moves into its red giant phase, it begins to expand, increasing in size and luminosity, profoundly altering the conditions of its surrounding environment. This change in stellar behavior can significantly impact the planets orbiting it, especially their habitability. Planets that were once comfortably situated within the habitable zone, the region where liquid water could exist on their surfaces, may now find themselves facing extreme temperatures that could make life unsustainable. The relationship between a star and its planets is a delicate, ever-evolving dance. Not only does the star influence the physical conditions of its orbiting planets, but it also has the potential to alter the very foundations necessary for life. These dynamics help us understand that the future of life, not only on Earth but elsewhere in the universe, hinges on the changes that occur within stars as they evolve. This cosmic cycle reminds us that the conditions for life in the universe are as transient as they are rare. One fascinating aspect of this celestial interaction is the phenomenon of tidal forces, particularly in the context of exoplanets, planets that exist outside our solar system. Tidal forces arise from the gravitational pull a star exerts on a planet, and as the planet orbits its star, different parts of it experience varying degrees of gravitational attraction. This differential force can have profound consequences on a planet's rotation, often leading to a phenomenon known as tidal locking. Tidal locking occurs when a planet's rotation slows down so much that one side of the planet always faces the star, while the other side is locked in eternal darkness. This effect is not just a theoretical curiosity, but a real phenomenon observed in many exoplanets. Tidal locking happens because of the persistent gravitational tug between a planet and its star, eventually causing the planet to rotate at the same rate that it orbits. The result is a planet with a permanent day side and a permanent night side. It's similar to how our moon is tidally locked to Earth, always showing the same face to our planet. However, tidal locking has broader implications beyond the synchronization of a planet's rotation. Over time, tidal forces can also affect the length of a planet's day. The gravitational interaction between the star and the planet slows the planet's rotation, gradually lengthening its day. This process, a subtle but constant tug of war, can span millions or even billions of years, leading to significant changes in the planet's environment. The extent of tidal effects depends on several factors. The proximity of the planet to its star is crucial. Planets that are close to their stars, particularly those within the habitable zone, are more likely to experience strong tidal forces. These forces can influence not only a planet's rotation, but also its climate, atmosphere, and overall habitability. Planets in this zone are often prime candidates for life because the temperatures are just right for liquid water to exist, but tidal interactions introduce complexities that scientists must consider when evaluating a planet's potential to support life. When scientists assess the habitability of exoplanets, they focus on several key factors. The most important of these is the planet's location within the star's habitable zone. Known as the Goldilocks zone, this region is where temperatures are neither too hot nor too cold for liquid water to exist on the planet's surface. Water is essential for life, making this a critical criterion for habitability. However, being in the habitable zone is not enough. The presence of a suitable atmosphere is another vital factor. The atmosphere must contain essential gases such as oxygen and carbon dioxide, while also providing protection from harmful radiation and maintaining a stable pressure. The planet's size and mass are also important. Ideally, habitable exoplanets should be rocky, terrestrial planets similar to Earth, rather than gas giants. Rocky planets are more likely to have the right conditions for life, including the ability to retain an atmosphere and support liquid water. A planet's size is critical in this regard. Planets that are too small may not have enough gravity to keep their atmospheres intact over time, while larger planets may have excessive gravity or thick atmospheres that make life unlikely. In addition to these fundamental factors, scientists also consider the presence of geological activity and magnetic fields. Geological activity can recycle nutrients and stabilize a planet's climate, while magnetic fields protect the surface from harmful radiation. Together, these factors provide a more comprehensive picture of a planet's environment and its potential to support life. Recent discoveries have radically shifted our understanding of where life might thrive beyond Earth. For decades, scientists focused primarily on finding Earth-like planets in the Goldilocks zone, believing that only planets with similar conditions to our own would be capable of supporting life. However, recent advancements in technology have broadened this search. Telescopes like Kepler and TESS, Transiting Exoplanet Survey Satellite, have identified thousands of exoplanets, many of which reside in extreme environments. For example, planets orbiting red dwarf stars, stars that are smaller and cooler than our Sun, are becoming increasingly recognized as potential hosts for life. Despite their lower heat output, these stars can still support habitable zones around them, offering conditions suitable for life. Interestingly, moons of gas giants within our own solar system are also gaining attention as potential habitats for life. Moons like Europa, one of Jupiter's moons, and Enceladus, a moon of Saturn, have subsurface oceans beneath their icy crusts. These oceans, warmed by tidal forces from their parent planets, could harbor life, possibly even microbial organisms, shielded from the harsh conditions of space. The discovery of plumes of water vapor and organic compounds erupting from Enceladus has sparked excitement among scientists, suggesting that life could exist in these hidden, frigid oceans. Even more surprising are the possibilities for life in environments previously considered hostile, such as Venus. In recent years, scientists have detected traces of phosphine gas in Venus's atmosphere, a compound that on Earth is associated with biological processes. This finding suggests that life might exist in the acidic clouds of Venus, despite the planet's extreme surface temperatures. These revelations have opened up new avenues for exploration and discovery, like showing that life could exist in a variety of environments, many of which were once considered inhospitable. This growing body of evidence expands the definition of habitability and challenges our assumptions about where life might thrive. When we think about the ingredients necessary for life, we typically consider water, warmth, and a stable environment. However, scientists are increasingly exploring the possibility that life could survive in far harsher conditions than we previously thought. One intriguing area of research involves extreme temperatures. Hydrothermal vents on Earth's ocean floor, where life flourishes in the intense heat, offer a glimpse into how life could adapt to even hotter environments. Planets like Venus, with surface temperatures reaching hundreds of degrees Celsius, could potentially harbor life forms that have evolved to withstand such extremes. On the other end of the spectrum are the cold, distant worlds like Europa, which is believed to have a subsurface ocean insulated by a thick layer of ice. These oceans could harbor life forms that rely on chemical energy from the ocean floor, much like the deep-sea ecosystems on Earth that thrive without sunlight. Such environments challenge our preconceptions about the conditions under which life can exist, suggesting that life could thrive in places we once thought were too extreme to support any form of existence. In this vast and ever-changing universe, we are only beginning to scratch the surface of the many possibilities for life beyond Earth. Each new discovery adds another layer of complexity to our understanding of habitability, reminding us that the universe is full of surprises, and the potential for life may be far greater and more diverse than we ever imagined. Imagine life flourishing in the most unforgiving and acidic environments, far beyond the bounds of what we consider livable. On Earth, certain extremophiles, organisms that thrive in extreme conditions, have adapted to survive in highly acidic lakes, soils, and even volcanic environments. These life forms challenge our basic assumptions about where life can exist. Could life, in microbial forms or even more complex structures, thrive in environments of exoplanets with thick atmospheres composed of carbon dioxide, sulfuric acid, and other harsh chemicals? The very existence of these organisms here on Earth suggests that life may find a way to survive even in conditions far removed from the familiar. In the search for life beyond Earth, humanity's definition of habitability is being stretched in ways that once seemed unimaginable. What we know about the resilience of Earth's organisms opens up the tantalizing possibility that life, against all odds, could persist and even evolve in environments that seem inhospitable by earthly standards. As we study the extremophiles on our planet, we gain valuable insight into how life could survive and adapt in the farthest reaches of space. One of the most captivating examples of this is the discovery of hot Jupiters, a class of exoplanets that bear some striking similarities to our own Jupiter, yet exist in an entirely different and much harsher environment. These gas giants are massive, much like Jupiter, but their close orbits to their parent stars expose them to extreme temperatures, often exceeding 1,000 degrees, 1,832 degrees Fahrenheit. This intense heat radically alters their atmospheres, leading to conditions unlike any we encounter in our solar system. Traditionally, scientists believed that gas giants formed far from their stars in cooler regions where gases could coalesce into large planetary bodies. However, the discovery of hot Jupiters has forced scientists to rethink this theory. These planets appear to have migrated from the colder outskirts of their star systems toward the scorching orbits they occupy today. This migration process offers intriguing insights into planetary dynamics, including how solar systems evolve over time. The atmospheres of hot Jupiters are among the most extraordinary features of these worlds. Their extreme heat and proximity to their stars cause unique chemical processes that may not occur elsewhere. Scientists have found a variety of compounds and elements in their atmospheres, including water vapor, carbon monoxide, and even signs of clouds and hazes. These findings provide an unprecedented opportunity to study the chemistry of far-off planets in ways we never thought possible, deepening our understanding of the forces that shape planetary atmospheres. While hot Jupiters themselves may not be habitable, they serve as invaluable laboratories for studying planetary atmospheres under extreme conditions. Observing the weather patterns, chemical processes, and atmospheric behaviors of these gas giants offers clues to the broader question of life in the universe. In particular, the study of these extreme environments gives us insight into how conditions on other worlds might support life, whether microbial or more complex. The temperatures on hot Jupiters present a stark contrast to the much colder gas giants in our own solar system. For instance, while Jupiter's average temperature hovers around 9 to 20 degrees Fahrenheit, 9 to 29 degrees Celsius, hot Jupiters experience surface temperatures that can soar above the 2,000 degrees Fahrenheit, 1,093 degrees Celsius. This temperature difference arises from the planet's proximity to their stars. Hot Jupiters orbit much closer than Mercury, the closest planet to the Sun, enduring intense solar radiation. Their thick atmospheres, primarily composed of hydrogen and helium, create a phenomenon known as thermal inversion. This occurs when temperatures increase with altitude instead of cooling as they do on Earth. This inversion creates a blistering upper atmosphere where winds can reach extraordinary speeds and contribute to chaotic weather patterns unlike anything seen in our solar system. These extreme conditions also give rise to unusual chemical reactions in the atmosphere. High temperatures allow for the presence of exotic molecules such as sodium and potassium, which would be vaporized at lower temperatures. As a result, these planets may have bizarre cloud formations, potentially composed of metals vaporized in the searing heat. The possibility of such strange atmospheric phenomena invites a rethinking of planetary chemistry and the processes that govern planetary atmospheres across the universe. As we continue to explore hot Jupiters, we find that they not only expand our understanding of how gas giants form and evolve, but also challenge our imagination. These distant worlds stretch the boundaries of what we once thought was possible in terms of planetary atmospheres. While our solar system's gas giants, like Saturn and Uranus, are cold and distant, hot Jupiters offer a glimpse into the incredible variety of planetary environments that may exist throughout the cosmos. The study of hot Jupiters also reveals important information about atmospheric loss, a process that occurs when the intense heat from the star strips away a planet's atmosphere. This phenomenon, known as atmospheric escape, happens when the energy from the star excites the gases in the planet's atmosphere, causing them to reach escape velocity and dissipate into space. Observations of this process have shown that hot Jupiter's atmospheres can change dramatically over time due to this loss. This finding is crucial for understanding the dynamics of planetary atmospheres and raises important questions about the potential habitability of smaller, Earth-like planets that may reside in the same star systems. By studying hot Jupiters, we are learning not just about these extreme worlds, but also about the fundamental processes that shape all planetary systems, including our own. While these planets may seem inhospitable, they provide invaluable insights into the formation of planets, the behavior of planetary atmospheres, and the ways in which life might survive, even in the most unlikely of places. As we continue our exploration of the cosmos, the lessons we learn from these exotic worlds will help us refine our search for life elsewhere in the universe. These investigations provide profound insights into the intricate processes that shape planetary evolution, especially regarding the ability of planets to retain their atmospheres. This critical factor can substantially influence a planet's future habitability, dictating whether it remains a cradle for life or becomes a barren wasteland. When a planet orbits too close to its star, like the case of hot Jupiters, its atmosphere can be rapidly stripped away by intense stellar radiation. Over time, this leads to an inhospitable environment devoid of the conditions necessary for life to thrive. However, the picture changes when a planet is situated further from its star, where it can hold onto a thicker atmosphere, one rich in the elements essential for life. Such atmospheres can create conditions that sustain liquid water, regulate temperatures, and protect from harmful radiation, thus making these worlds more conducive to life. Understanding the processes that determine whether a planet can retain its atmosphere is not only critical for comprehending the fate of hot Jupiters, but also provides a valuable framework for evaluating the habitability of exoplanets across the cosmos. In fact, the study of hot Jupiters reveals much more than the future of these massive, gaseous worlds. It offers a window into the broader workings of planetary systems, how they form, evolve, and ultimately support or inhibit life. Through these investigations, scientists are piecing together the complex puzzle of planetary evolution. The ultimate goal remains the same: to understand what makes a world capable of supporting life. This pursuit, while driven by curiosity, has occasionally led to groundbreaking revelations that stretch the limits of our imagination, revealing just how much we still have to learn about the universe and our place within it. Among the most intriguing categories of exoplanets are super-Earths, planets that are notably larger and more massive than Earth, but are smaller than gas giants. These celestial bodies present fascinating opportunities for studying planetary composition, geological activity, and potential habitability. Super-Earths typically possess masses ranging from 2 to 3 times that of Earth, a characteristic that places them in a unique zone where gravitational forces have significant effects on their atmospheric and geological properties. This makes them incredibly diverse in terms of both composition and potential environments, leading to compelling questions about what kinds of ecosystems they could host. While many super-Earths reside within their star's habitable zone, where conditions could allow for the presence of liquid water, they are vastly different from Earth in several key ways. Unlike our planet, which is predominantly rocky, some super-Earths are likely gas giants with thick atmospheres that could envelop solid cores. This variation opens up new possibilities in terms of geological activity and climate patterns. Imagine planets with vast oceans where the immense pressure in their interiors might create metal-rich landscapes, or worlds where exotic forms of geology and perhaps even alien ecosystems might emerge. These planets could be utterly unlike anything we've seen in our own solar system, offering tantalizing glimpses into what life might look like in environments very different from Earth. Furthermore, the atmospheric compositions of super-Earths are incredibly diverse. Some may possess thick clouds of gases, like carbon dioxide or methane, leading to intense greenhouse effects and scorching temperatures. Conversely, others might have conditions that closely mirror Earth's, potentially supporting liquid water and even life. This raises intriguing questions. What kinds of life could arise on planets where conditions, though potentially similar to Earth, differ so dramatically in other ways? The study of super-Earths challenges our understanding of what constitutes a habitable world and spurs us to imagine the possibilities for life beyond our home planet. The discovery of water, whether in liquid or vapor form, on super-Earths could revolutionize our understanding of habitability. Water is a fundamental ingredient for life as we know it, and its presence expands the potential for finding life beyond Earth. In particular, super-Earths offer a diverse range of possibilities for water's existence. These planets often reside in the habitable zone around their stars, a region where temperatures are just right for liquid water to remain stable on their surfaces. However, the habitable zone is not a fixed region. It shifts depending on the type of star and the planet's atmosphere, making the study of water on super-Earths a constantly evolving field of research. Moreover, the detection of water vapor can also be a sign of active geological processes, hinting at the possibility of weather systems or volcanic activity. If water vapor is found in significant quantities, it may indicate that a planet has a thick, dynamic atmosphere capable of sustaining complex weather systems. This could, in turn, suggest that the planet's surface conditions might be suitable for life. Such discoveries fuel not only scientific curiosity, but also the potential for future exploration, as we seek to understand more about these distant worlds and the broader universe they inhabit. The existence of super-Earths with water in particular is a powerful reminder that we are not alone in our quest for life beyond Earth. These planets serve as beacons in our search for other life forms and offer a unique opportunity to explore planetary formation and evolution on a grander scale. As we refine our methods of detecting and analyzing these distant worlds, we not only expand our knowledge of how planets come into being, but also broaden our understanding of the conditions necessary for life to flourish. In many ways, super-Earths serve as the perfect laboratory for exploring the diversity of planetary systems. These celestial bodies fall between the sizes of Earth and Neptune, and their greater mass gives rise to higher gravity, which has significant implications for both their atmospheres and the physical conditions on their surfaces. Increased gravity allows for a denser atmosphere, which in turn can stabilize the planet's climate, a critical factor for the development of life. A thick atmosphere can help regulate temperatures, create a protective shield from harmful cosmic radiation, and maintain the delicate balance needed for life to exist. In the search for habitable worlds, super-Earths stand out not only because of their size and composition, but also because they demonstrate that life may not necessarily require a planet exactly like Earth to take root. Instead, these planets challenge our perceptions of what a habitable world could be, opening up new frontiers in the search for life beyond our solar system. As scientists continue to explore these fascinating worlds, they are not just expanding our understanding of planetary evolution, they are also deepening our understanding of the very essence of life itself. The ability to maintain a life-supporting atmosphere on a planet over long periods of time is a delicate balance. This balance hinges on two primary factors: the planet's geological activity and its magnetic field. Both of these crucial elements can be influenced by the planet's size and gravitational pull. However, the very factors that enable a stable atmosphere, such as the planet's gravity, also introduce their own set of challenges. Increased gravity, for instance, might restrict the mobility and overall size of organisms. On a planet with higher gravity, life forms may evolve to become more compact and resilient, adapting to the weight of their environment. Such creatures could resemble Earth's deep-sea organisms, known for their dense, stocky builds, rather than the more elongated forms we typically observe on land. The evolutionary pressures exerted by higher gravity might reshape the structure and behavior of life in unexpected ways. While increased gravity could enhance the likelihood of sustaining a life-friendly atmosphere, it also creates unique challenges for life to adapt and survive. This raises the exciting possibility that the forms life could take on other worlds may be radically different from what we're familiar with. As scientists continue to explore exoplanets, planets orbiting stars beyond our solar system, the question of how life might adapt to these extreme conditions remains at the forefront of research. Each discovery opens a new chapter, further enriching our understanding of how life might manifest in the vast reaches of the universe. In the search for life beyond Earth, the concept of an ocean world offers a compelling avenue of investigation. Ocean worlds are celestial bodies, often moons or distant exoplanets that possess significant quantities of liquid water, typically buried beneath thick, icy crusts. The discovery of subsurface oceans on these worlds suggests that they could harbor the conditions necessary for life. Water, as we know, is the key ingredient for life. The mere presence of liquid water makes these worlds particularly enticing in the search for extraterrestrial life. One of the most intriguing examples of an ocean world in our own solar system is Europa, a moon of Jupiter. Evidence of its hidden ocean is abundant, from the moon's surface, which shows signs of being dynamically altered by a liquid layer beneath, to the magnetic data collected by spacecraft like Galileo. These findings suggest that Europa's ocean could be as deep as 100 miles in some regions. What's even more exciting is that scientists believe the interaction between Europa's subsurface ocean and its rocky ocean floor could create the right conditions for life, similar to the hydrothermal vents we find on Earth's ocean floor, places where life thrives in extreme conditions. Another notable example is Enceladus, a small moon of Saturn. Enceladus has become a prime target for astrobiologists due to its active geysers, which shoot water vapor and ice particles into space. These plumes, analyzed by the Cassini spacecraft, not only contain water but also organic molecules, a fundamental building block for life. The discovery of these compounds suggests that Enceladus might have the right conditions to support microbial life, providing further evidence that life could exist in places we had once thought inhospitable. Beyond our own solar system, the search for ocean worlds takes on a broader scale. Numerous exoplanets, particularly those within the habitable zones of their stars, have been identified as possible ocean worlds. These exoplanets are often characterized by the presence of water vapor in their atmospheres, as well as by models of their potential geological and heat sources. The idea that life could exist beneath the icy crusts of distant moons or planets expands the possibilities for life to thrive in environments vastly different from anything we experience on Earth. The discovery of a subsurface ocean on an exoplanet would be a monumental step forward in the search for extraterrestrial life. Oceans are not just a source of water. They are dynamic ecosystems that support life by allowing nutrients to circulate and complex chemical reactions to occur. If an exoplanet possesses an ocean beneath its surface, it could provide a stable and nourishing environment where life could evolve and thrive, even in places where surface conditions may seem hostile or barren. This shift in focus, from planets with liquid water on their surfaces to those with hidden oceans beneath thick ice layers, could dramatically expand the range of potential habitats for life beyond Earth. As we delve deeper into this research, we come to appreciate the potential of these ocean worlds. The icy moons in our solar system, like Europa and Enceladus, are just the beginning. Their subsurface oceans, hidden beneath thick, icy exteriors, hold the tantalizing possibility of life thriving in environments that, on the surface, would seem inhospitable. The discovery of similar exoplanets, planets with vast subsurface oceans, could offer insights into ecosystems that are entirely alien to us, opening new possibilities for life on other worlds. Furthermore, the search for life may soon take a new direction by focusing on the chemical signatures emitted by these subsurface oceans. On Earth, microbial life thrives in extreme environments such as deep-sea hydrothermal vents and acidic hot springs. If we detect organic compounds or gases that indicate biological processes in the atmospheres of distant worlds, it could provide the first signs of life beyond our planet. This opens up exciting new research avenues in astrobiology as we shift our focus to these hidden watery realms. By extending our criteria for life-supporting environments to include planets with subsurface oceans, we cast a wider net in the search for extraterrestrial life. As we explore the depths of our own solar system and beyond, we begin to understand that life may not only exist in the familiar, Earth-like conditions we once thought necessary, but could also thrive in environments vastly different from our own. The discovery of life on ocean worlds, whether within our own solar system or on distant exoplanets, would mark a major milestone in humanity's quest to understand the vast and mysterious universe. The implications of finding exoplanets with multiple oceans, worlds where water exists in more than one place, are profound. Such planets would likely possess a complex and dynamic environment, creating a diversity of habitats and ecological niches. Much like Earth, which hosts a wide range of environments from warm, tropical seas to cold polar waters, these multiple oceans could foster a greater variety of life forms. Each ocean could have unique characteristics such as variations in temperature, salinity, and chemical composition, which would influence the types of life that could evolve. The interplay between these distinct oceans could lead to a more intricate web of biological and geological interactions, offering exciting possibilities for the development of life. The potential for multiple distinct ecosystems on a single planet increases the odds that life could evolve in different forms, fostering diversity in ways we may not yet fully understand. As we continue our search for life beyond Earth, the discovery of planets with multiple oceans would not only expand our understanding of where life could exist, but also reshape our view of what life could look like in the cosmos. Moreover, the presence of more than one ocean on a planet could have a profound impact on its climate and weather patterns. Oceanic circulation, the process by which oceans move and redistribute heat, plays an indispensable role in regulating temperatures across the globe and in distributing vital nutrients to ecosystems. If an exoplanet harbors multiple oceans, their interactions could be far more intricate than those found on Earth, leading to complex climate systems that influence everything from storm formation to the availability of crucial elements necessary for life. These oceans might serve as interconnected drivers of the planet's weather systems, shaping patterns of rainfall, atmospheric pressure, and wind circulation. This sort of environmental richness, where oceans and atmospheric systems influence each other in dynamic ways, could potentially give rise to more diverse and robust ecosystems. These ecosystems, in turn, might provide the necessary stability for life to not only survive, but thrive over extended periods. Such environments could offer conditions that support a wide range of life forms, allowing for evolution to take place in ways we have yet to imagine. The discovery of exoplanets with multiple oceans thus holds exciting potential for our understanding of habitability in the universe. It challenges our preconceived notions about what makes a planet capable of supporting life. As our methods of discovering and studying distant worlds continue to advance, we may come to realize that the universe is full of planets with environments we never thought possible, each offering new opportunities for life to exist in forms we've never considered. Rogue planets, for example, are one such mysterious class of celestial bodies. These planets wander through space without being tethered to any star, drifting freely through the galaxy. Unlike typical exoplanets that orbit around stars, rogue planets have been either ejected from their original solar systems or have formed in isolation, far from the gravitational influence of a host star. This means they travel through the vast dark reaches of space, potentially never receiving the warmth or light of a sun. One of the most captivating features of rogue planets is their sheer mystery. Some astronomers speculate that there could be more rogue planets than stars in our galaxy, which opens up new questions about the nature of planetary formation and the conditions that allow for such worlds to exist. These planets can vary greatly in size and composition, much like planets that orbit stars. Some may be large, gas-filled giants similar to Jupiter, while others could be rocky, Earth-like bodies. The key distinction is that rogue planets, without the energy of a nearby star, are often subjected to extreme cold, making their surfaces likely inhospitable to life as we know it. Yet the existence of rogue planets presents a fascinating puzzle. Despite the lack of sunlight and warmth, these worlds could still harbor life, albeit in ways that we might find difficult to imagine. Scientists propose that rogue planets could maintain internal heat generated by geothermal activity or radioactive decay. This heat might provide enough warmth beneath the planet's icy crust to form subsurface oceans or to create an atmosphere that could support life. In some cases, rogue planets might have atmospheres composed of gases like hydrogen or methane, which could foster the chemical processes necessary for life. The potential for life on rogue planets raises intriguing questions about the nature of habitability. While the surface conditions of these planets may appear to be uninhabitable, internal processes could create stable environments that support life beneath the surface or in the atmosphere. For example, life could take the form of microbial organisms living in liquid water beneath frozen surfaces or in heated pockets within the planet's interior. Such environments challenge our traditional understanding of where life can exist and what forms it might take. The study of rogue planets is still in its early stages, but as technology continues to advance, astronomers are developing new methods to detect these enigmatic worlds. Each discovery of a rogue planet adds another layer of understanding to our growing knowledge of the universe. It reminds us that life could exist in places far beyond the reach of starlight, offering new possibilities for exploration and discovery. Rogue planets also provide valuable insights into the processes of planetary formation and evolution. Unlike planets that orbit stars, rogue planets have either been expelled from their original systems or formed in isolation. This distinction makes them invaluable to scientists seeking to understand the different ways in which planets can come into being. By studying rogue planets, researchers can test various theories about planetary formation in diverse environments, shedding light on the conditions that give rise to planetary bodies in the first place. Rogue planets could also hold remnants of their formation history, providing clues about the materials and processes that contributed to their development. This information might challenge or reinforce existing models of planetary formation, offering new perspectives on how planets evolve over time. In some cases, studying rogue planets could reveal how planets adapt to the lack of a star and how they sustain their atmospheres or retain any potential for life. By examining these worlds, scientists can broaden their definition of habitability, showing that planets can adapt to even the harshest of conditions. Furthermore, the discovery of rogue planets suggests that there may be far more of them than previously thought, potentially outnumbering the stars in our galaxy. This abundance of rogue planets challenges the traditional view of planetary systems, highlighting the diversity of planetary outcomes in the cosmos. Each rogue planet discovered provides another piece of the cosmic puzzle, helping astronomers piece together the history of our universe and refine our understanding of how planetary systems evolve. The technological advancements that have taken place in recent decades have revolutionized our ability to discover and study exoplanets, planets located outside our solar system. Just a few decades ago, the existence of these distant worlds was largely theoretical. Today, thanks to cutting-edge technology and innovative methods, we have confirmed the existence of thousands of exoplanets, expanding our understanding of the universe and our place within it. One of the most significant developments in exoplanet discovery was the launch of the Kepler Space Telescope in 2009. Kepler used a method known as the transit technique to detect exoplanets. By monitoring the brightness of stars, Kepler was able to detect the faint dips in light that occur when a planet passes in front of its host star. This breakthrough led to the discovery of over 2,500 exoplanets during Kepler's mission, which ended in 2018. These discoveries have had profound implications for our understanding of the cosmos. They have broadened our conception of what is possible in the universe, showing us that planets can exist in environments we never imagined. With continued advancements in space exploration and technology, it is likely that we will find many more exoplanets in the years to come, further expanding our understanding of the infinite possibilities that exist in the universe. The study of exoplanets, planets that orbit stars beyond our solar system, has witnessed tremendous growth in recent years, reshaping our understanding of the cosmos and our place within it. Once thought to be a solitary system, our solar system is now recognized as one among countless others, each potentially harboring planets with environments suitable for life. The advent of new technologies such as advanced spectrometry and artificial intelligence, combined with the groundbreaking capabilities of telescopes like the James Webb Space Telescope, has greatly enhanced our ability to discover and study these distant worlds. One of the most significant advancements in the field is the development of spectrometry, a technique that has revolutionized the way scientists study the atmospheres of exoplanets. By analyzing the light that filters through a planet's atmosphere as it transits in front of its star, astronomers can determine the chemical composition of that atmosphere. This method has proven invaluable in providing key insights into the potential habitability of exoplanets, revealing the presence of vital elements such as water vapor, carbon dioxide, and even methane, gases that are often associated with biological processes on Earth. Such discoveries help scientists assess whether a planet could potentially support life. In recent years, ground-based observatories have also made remarkable strides by adopting larger telescopes equipped with advanced adaptive optics. This technology corrects the blurring effects of Earth's atmosphere, enabling astronomers to observe exoplanets with much greater clarity. By combining advancements in both space and ground-based technologies, our ability to discover and study exoplanets continues to grow, bringing us closer to understanding the conditions necessary for life beyond Earth. Artificial intelligence, AI, has emerged as another game-changing tool in the search for exoplanets. The vast amounts of data generated by telescopes and space missions make it increasingly difficult for human scientists to manually analyze all the information. AI can sift through these immense datasets quickly and efficiently, identifying subtle patterns and anomalies that might otherwise go unnoticed. For example, small dips in a star's brightness, indicating the passage of an exoplanet in front of the star, can be detected with greater precision using AI-powered algorithms. Machine learning algorithms, a subset of AI, have shown remarkable promise in improving the detection of exoplanets. These algorithms are trained using data from known exoplanets, enabling them to recognize unique signatures associated with planetary transits. This allows AI to categorize and prioritize potential exoplanet candidates for further investigation, dramatically accelerating the research process. In fact, AI has even uncovered new planets in historical data that had previously been overlooked by human scientists. Beyond detection, AI also plays a crucial role in analyzing the atmospheric composition of exoplanets. By studying the light passing through a planet's atmosphere, AI helps interpret spectral data to identify chemical signatures, such as those of water vapor, carbon dioxide, or methane. This analysis is essential for evaluating whether an exoplanet could support life. The integration of AI into exoplanet research is transforming the way we study these distant worlds. As AI technologies continue to evolve, they promise to revolutionize our understanding of exoplanets and bring us closer to answering one of humanity's most profound questions. Are we alone in the universe? Meanwhile, the James Webb Space Telescope, JWST, often referred to simply as Webb, is set to take our exploration of exoplanets to an entirely new level. Unlike its predecessors, Webb is capable of observing the universe in infrared light, a feature that allows it to peer through cosmic dust and gas that often obscure celestial objects from view. This ability is particularly valuable when studying the atmospheres of distant exoplanets, as Webb can reveal hidden details about these worlds, such as their chemical composition and potential for habitability. What truly sets Webb apart is its unprecedented sensitivity and resolution. Equipped with state-of-the-art instruments, the telescope can detect incredibly faint light from distant star systems, allowing astronomers to study the atmospheres of exoplanets in unparalleled detail. By observing the chemical makeup of a planet's atmosphere, scientists can gain valuable clues about the planet's potential to support life. For instance, the presence of certain gases like oxygen, methane, or carbon dioxide might suggest the possibility of biological processes, sparking our imaginations about the existence of life beyond Earth. Webb is also designed to focus on planetary systems that resemble our own, making it an invaluable tool for studying star and planet formation. By observing different stages of the evolution of planetary systems, Webb offers a unique opportunity to refine our models of how planets form and develop over time. Each new discovery promises to deepen our understanding of the universe, revealing its vast diversity and shedding light on the many ways planets and stars can evolve. The James Webb Space Telescope represents a monumental leap forward in our scientific capabilities. By unlocking the secrets of distant exoplanet atmospheres and examining their formation and evolution, Webb not only advances our knowledge of these distant worlds, but also enhances our broader understanding of the universe. Each observation made by Webb fuels a cycle of discovery and curiosity, pushing the boundaries of what we know and inspiring new questions that may one day reshape our understanding of life in the cosmos. The discovery of exoplanets has profoundly altered our view of the universe. Just a few decades ago, we believed our solar system was a rare and unique phenomenon. Now, astronomers have confirmed the existence of over 5,000 exoplanets, each orbiting stars far beyond our own. This realization has transformed our perception of the cosmos, revealing that planetary systems are not rare, but rather common throughout the universe. Some of these planets orbit their stars at blazing hot distances, while others are situated in the frigid reaches of space. Yet, many exoplanets reside within the habitable zone of their stars, regions where conditions are just right for liquid water to exist on the surface, an essential ingredient for life as we know it. These discoveries suggest that the ingredients for life may be far more widespread than we previously imagined, raising hopes that one day we might find extraterrestrial life. With each new exoplanet found, we are one step closer to answering the age-old question of whether we are truly alone in the universe. And as technology continues to advance, our ability to study these distant worlds will only improve, bringing us ever closer to discovering the truth about life beyond Earth. In the end, the quest to find exoplanets and possibly even life will continue to drive exploration and scientific innovation for generations to come. As we unveil more secrets of these distant worlds, we are not just uncovering new planets, we are discovering our place in the vast, ever-expanding universe. The discovery of exoplanets, planets that orbit stars outside our solar system, has opened up an entirely new realm of possibilities, challenging long-held beliefs about habitability and the very nature of life. Some of these distant worlds possess atmospheres unlike anything we know on Earth. They may feature clouds of vapor and gases that could support alien ecosystems, unlike anything in our terrestrial experience. These discoveries force us to reevaluate our understanding of what constitutes life and where it might thrive. They beckon us toward the tantalizing idea that life could exist in forms entirely beyond our imagination, prompting us to ask not only whether life exists beyond Earth, but what that life might look like. This realization redefines our place in the cosmos. No longer are we isolated in an empty universe, but instead we are part of a rich, dynamic environment teeming with potential neighbors, each one with its own unique conditions and stories yet to be discovered. This exciting possibility fills us with both humility and optimism, encouraging us to reflect on our own existence in the context of a larger, more interconnected universe. The future of space exploration holds the promise of unimaginable discoveries, reminding us that there is still so much left to learn. Throughout history, humanity has been captivated by the stars, giving rise to countless myths and stories about life beyond our world. From ancient civilizations to modern-day scientific endeavors, the quest to understand the cosmos has always been intertwined with our deepest hopes and dreams. Across cultures, these tales reflect our innate curiosity and longing for connection, and weaving together cosmic elements with the possibility of extraterrestrial life. In ancient Mesopotamia, for example, the Sumerians believed in a pantheon of gods who hailed from the heavens. The Anunnaki, as they were known, were thought to have descended from the stars to shape humanity and impart their wisdom. This early belief system not only connected deities with the cosmos, but also laid the foundation for later ideas about celestial visitors, concepts that resonate with our modern search for life on distant planets. Similarly, many indigenous cultures across the Americas have their own unique interpretations of the stars and what lies beyond them. The Hopi people, for instance, speak of the Kachinas, spiritual beings who inhabit the stars and bring life to Earth. Their mythology emphasizes themes of balance and harmony, suggesting that life is not confined to our planet, but is part of a broader, interconnected cosmic web. This belief encourages a respectful and reverent view of the universe, fostering the idea that life, wherever it may exist, is fundamentally linked to life on Earth. As humanity's technological capabilities advanced, these ancient myths evolved into more sophisticated inquiries into the nature of extraterrestrial life. The modern fascination with UFOs and the search for intelligent civilizations, whether through signals from distant stars or the study of exoplanets, echoes these ancient tales, while grounding them in scientific inquiry. Today, we continue to search for answers that our ancestors could only speculate upon. And as we do so, we are reminded that the quest for knowledge is a timeless journey, one that transcends cultural and historical boundaries. The discovery of exoplanets has only intensified this sense of wonder and curiosity. With new technologies and techniques such as space telescopes and advanced imaging methods, scientists are unveiling a growing catalog of distant worlds. These discoveries not only captivate the public imagination, but also raise important questions about our place in the universe. The sheer variety of exoplanets, each with its own set of conditions, forces us to rethink what makes a planet habitable and whether life in some form might thrive under conditions vastly different from our own. As public interest in exoplanets continues to grow, so too does support for astronomical research. Governments, private organizations, and individuals recognize the value of these discoveries, which have profound implications for science and for our understanding of life in the universe. When the public is excited about the potential for finding Earth-like planets, funding for space missions and supporting technologies tends to increase. This in turn drives further exploration and technological advancement, creating a feedback loop of curiosity, investment, and discovery. Moreover, exoplanet research is more than just a scientific pursuit. It has sparked broader cultural conversations about science and technology. Documentaries, articles, and social media have helped spread the stories of these distant worlds, creating a collective sense of wonder and awe. Major milestones such as the discovery of water on exoplanets or the detection of potential biosignatures generate excitement and stimulate public interest, leading to educational initiatives and science outreach programs. This cultural shift toward valuing scientific inquiry ensures that more people are engaged in and invested in the ongoing search for knowledge about our place in the universe. In response to this growing public interest, collaborations between universities, space agencies, and private enterprises have become more common. As these partnerships grow, so too does the appetite for innovative research that could yield groundbreaking discoveries. Every new exoplanet discovered offers new insights into the universe, deepening our understanding of planetary systems, the conditions necessary for life, and the processes by which planets form and evolve. As we learn more about exoplanets, we also learn more about our own planet, fueling an enduring cycle of curiosity, exploration, and discovery. Several upcoming missions and technologies promise to significantly enhance our understanding of exoplanets in the years to come. One of the most anticipated is the James Webb Space Telescope, launched in December 2021. This state-of-the-art instrument is designed to observe exoplanets in unprecedented detail, with a particular focus on their atmospheres. By analyzing the light that passes through an exoplanet's atmosphere during a transit, when the planet moves in front of its host star, scientists can identify the presence of key molecules such as water vapor, carbon dioxide, and possibly even signs of life. Beyond the Webb telescope, the European Space Agency is preparing the Ariel spacecraft, which is set for launch in 2029. Ariel's mission will involve surveying a large number of known exoplanets, with an emphasis on their compositions and atmospheric conditions. By studying over 1,000 exoplanets, Ariel aims to provide a comprehensive understanding of how distant worlds form and evolve. The data collected by Ariel could reveal patterns that had helped scientists understand the diversity of planetary systems and the conditions that may give rise to life. Each new discovery about exoplanets brings us closer to answering some of the most profound questions about life in the universe. As our technology advances and our understanding of the cosmos deepens, we move ever closer to the day when we may be able to answer, once and for all, whether we are truly alone in the universe. Until then, the search for exoplanets continues to inspire wonder, curiosity, and hope for the future of space exploration. The exploration of exoplanets, planets that orbit stars outside our solar system, is rapidly evolving, and groundbreaking technological advancements are continually reshaping our approach to this fascinating field. With every new development, scientists are unlocking more secrets about distant worlds, transforming our understanding of the cosmos and the potential for life beyond Earth. One of the most remarkable advances in ground-based astronomy is the construction of the Extremely Large Telescope, ELT, in the Chilean Andes. When completed, this telescope will feature a mirror nearly 39 meters in diameter, making it one of the most powerful instruments ever built. This enormous structure will significantly enhance our ability to directly image exoplanets and analyze their atmospheres, offering unprecedented views of distant worlds. By combining the ELT's immense power with advanced techniques like adaptive optics, which corrects for atmospheric distortions, astronomers hope to observe planetary details that were once deemed impossible. With such high-resolution imaging, scientists will be able to study exoplanets in ways that were unimaginable just a decade ago. In addition to the ELT, numerous smaller projects and emerging technologies are making waves in the world of exoplanet research. Artificial intelligence, AI, has become an indispensable tool for analyzing vast datasets collected from exoplanet surveys. By using sophisticated machine learning algorithms, scientists can identify patterns and signals in complex data that would be impossible to detect manually. This ability to process and interpret enormous amounts of information is revolutionizing the search for new exoplanets, enabling astronomers to pinpoint promising candidates for further study with greater precision and efficiency. The quest for Earth-like planets has also spurred the development of new techniques for detecting smaller rocky exoplanets, particularly those that might be similar to our own world. One of the most important methods used in this search is the transit method, in which astronomers monitor the brightness of distant stars for periodic dips in light. These dips occur when a planet passes in front of its host star, blocking a small portion of the light and revealing its presence. To improve the accuracy of this method, scientists are deploying more powerful space-based telescopes, which minimize the interference caused by Earth's atmosphere and enable the detection of even fainter signals from distant stars. Another innovative approach to discovering Earth-like exoplanets is the use of advanced imaging techniques. Telescopes equipped with specialized coronagraphs can block out the intense light of stars, allowing astronomers to see much fainter planets that orbit them. This technology, when combined with adaptive optics, significantly sharpens the images by compensating for distortions caused by Earth's atmosphere. Together, these techniques provide astronomers with clearer and more detailed views of planets that might be similar in size and composition to Earth, even in star-rich regions of the sky. Machine learning is also revolutionizing the analysis of data collected from missions like NASA's Kepler Space Telescope and the Transiting Exoplanet Survey Satellite, TESS. By employing algorithms to sift through enormous data sets, scientists can quickly identify potential exoplanet candidates that might have been overlooked using traditional methods. This not only speeds up the discovery process, but also increases the likelihood of finding Earth-like planets in the vast expanse of space. Looking ahead, the launch of powerful space telescopes such as the James Webb Space Telescope, JWST, and the upcoming Habitable Worlds Observatory promises to take exoplanet research to new heights. These instruments are designed to study the atmospheres of distant planets, searching for key indicators of habitability, such as water vapor or signs of chemical processes that could suggest the presence of life. With these advancements, astronomers are poised to make transformative discoveries about the potential for life beyond Earth and the conditions necessary for its existence. As we stand on the precipice of this new era of exploration, we must also confront the ethical considerations that come with the discovery and potential colonization of exoplanets. One of the most pressing issues is stewardship. If we were to discover life, no matter how simple, on a distant world, what responsibility do we have to protect and preserve these ecosystems? Introducing Earth-based organisms to alien environments could have unpredictable and irreversible consequences, potentially leading to the destruction of fragile extraterrestrial ecosystems. This raises profound questions about how we should approach the exploration of other worlds. Ownership and exploitation of exoplanets is another significant ethical concern. Throughout history, the exploration of new frontiers on Earth has often led to conflicts over resources, territory, and rights. The prospect of claiming ownership of exoplanets could give rise to similar disputes. Who has the right to settle on these planets or utilize their resources? Should exoplanets be considered a shared human heritage, or should certain nations or organizations hold dominion over them? These debates will shape the future of SpaceX exploration and may influence our collective values as a society. The technological advancements that drive space exploration also raise questions about the priorities we set on Earth. As we invest in the development of space exploration technologies, there is a risk of diverting attention and resources away from urgent global issues such as climate change, social inequality, and environmental degradation. While the potential for progress and innovation in space is vast, it is crucial to ensure that the pursuit of these goals does not come at the expense of addressing the pressing challenges facing humanity on Earth. Finally, we must consider the long-term implications of colonizing other worlds. Settling on exoplanets could have profound effects on our identity as Earthlings. What does it mean to be human if we begin to create permanent outposts beyond our home planet? This question touches on the core of our existence and forces us to reflect on our place in the universe. As we embark on this grand adventure into the cosmos, it is vital that we approach it with a sense of responsibility, ensuring that ethical exploration and the well-being of all life, both on Earth and beyond, are at the forefront of our efforts. Each of these questions about life, responsibility, and the potential for colonization serves as a mirror for humanity, reflecting our values, our ambitions, and our understanding of our place in the universe. The study of exoplanets is not just about discovering new worlds, but about understanding ourselves and the delicate balance of life that sustains us. By exploring the mysteries of the cosmos, we are forced to confront the larger questions about our origins, our future, and the future of life itself. Exoplanets are challenging and expanding our definitions of what makes a planet habitable, and by extension, what makes life possible. As astronomers discover thousands of these distant worlds, they are uncovering new insights into how the conditions necessary for life might arise elsewhere in the universe. One of the key factors in this search is the habitable zone, the region around a star where liquid water can exist. Water, as we know, is essential for life. It acts as a solvent for the biochemical reactions that sustain living organisms. By studying exoplanets in the habitable zone, researchers hope to identify environments that could support life, shedding light on the fundamental processes that make life possible. In addition to water, scientists are also focusing on the presence of other key elements, such as carbon and nitrogen, which are vital for life. Understanding the conditions under which life could emerge on different exoplanets offers clues about how life might have originated on Earth. The more we learn about the diverse environments on these distant worlds, the better we can understand the processes that led to the development of life on our own planet. The study of exoplanet atmospheres is another crucial aspect of this search for life. By analyzing the light that filters through a planet's atmosphere, astronomers can detect the presence of gases such as oxygen, methane, and carbon dioxide. These gases are of particular interest because they can indicate biological activity. For example, methane is often produced by living organisms on Earth, and its presence in the atmosphere of an exoplanet could suggest that something is actively generating it. By studying these gases, scientists can begin to form hypotheses about the possibility of life on distant worlds. The exploration of exoplanets not only brings us closer to the possibility of discovering extraterrestrial life, but it also deepens our understanding of the complex processes that sustain life on Earth. It reminds us of the delicate balance of conditions required for life to thrive and highlights the resilience of life itself. Even though life may be rare in the universe, the study of exoplanets suggests that it could also be incredibly adaptable, capable of thriving in diverse environments that were once thought inhospitable. The role of gravity is another important factor in this exploration. Gravity influences every aspect of a planet, from its physical characteristics to the potential life forms that might inhabit it. Each exoplanet's unique gravitational pull could shape the development of life in fascinating ways. On planets with stronger gravity, life forms might evolve to be denser and more robust to withstand the increased weight. For example, creatures might develop shorter, stockier bodies, similar to how some animals on Earth, such as frogs, adapt to denser environments. Conversely, on planets with weaker gravity than Earth's, life forms might evolve to be taller, lighter, or even capable of flight. Imagine creatures with elongated limbs or wings that enable them to glide through the air or travel long distances without tiring. The possibilities for life on exoplanets are endless, limited only by the unique conditions of each world and the adaptability of life itself. In the end, the study of exoplanets challenges us to rethink everything we know about life, our place in the universe, and the potential for discovery in the vast expanse of space. As technology continues to advance, our understanding of these distant worlds will only deepen, leading us to new revelations about the cosmos and our place within it. Gravity plays a pivotal role in shaping a planet's ability to support life, with far-reaching effects on its atmosphere, climate, and overall habitability. In particular, a planet's gravitational pull influences its capacity to retain gases that form the atmosphere, a vital component for sustaining life. In a low-gravity environment, a planet may struggle to maintain a thick atmosphere, which is crucial for regulating temperature and providing the essential elements for life. Without a dense atmosphere, the planet would be vulnerable to extreme temperature fluctuations, potentially making it unsuitable for life as we know it. On the other hand, a planet with a higher gravity can retain a much denser atmosphere, which could offer a more stable climate and create diverse ecosystems capable of thriving in the conditions it provides. Moreover, gravity's effects extend beyond just the atmosphere. The planet's gravity can influence various aspects of its environment, such as weather patterns, the movement of surface liquids, and geological activity. These factors, in turn, can create niches for a variety of life forms, supporting an intricate web of life, even in the most extreme conditions. For example, while Earth's gravity allows for a balanced weather system and reliable water cycles, other planets with different gravitational forces might have completely unique climates that challenge our preconceived notions of habitability. As we study these dynamics, our imaginations are sparked and the possibilities for life beyond our planet expand. The field of astrobiology, which seeks to understand the potential for life beyond Earth, becomes a critical tool in this exploration, urging scientists to venture further into the cosmos with renewed curiosity and excitement. Astrobiology is a multidisciplinary field that combines knowledge from biology, chemistry, geology, and astronomy to understand the fundamental requirements for life. By examining life on Earth, particularly the most resilient organisms, scientists can begin to identify the conditions and environments that could harbor life elsewhere. One of the central focuses of astrobiology is the search for extremophiles, organisms that survive in Earth's most hostile environments, such as in the boiling hot springs of Yellowstone, deep ocean hydrothermal vents, or the icy expanses of Antarctica. These life forms, capable of thriving under intense heat, pressure, or radiation, push the boundaries of what we consider habitable, suggesting that life could exist in places previously thought inhospitable. This realization broadens the scope for where life might emerge beyond Earth. Moons like Europa, with its subsurface ocean, or Enceladus, which periodically ejects plumes of water vapor, are now considered more promising candidates for life than ever before. These environments could harbor ecosystems beneath their icy crusts, where liquid water might be present, protected from the harsh conditions of the surface. In addition, astrobiologists are increasingly focused on identifying biosignatures, specific indicators of life, that could be detected in the atmospheres of distant planets. Gases like oxygen, methane, and carbon dioxide can be telltale signs of biological activity. As technology improves, particularly with the advent of powerful telescopes like the James Space Telescope, scientists are gaining the ability to analyze the atmospheres of exoplanets, refining predictions about which worlds might support life. Ultimately, astrobiology serves as the roadmap for our search for life in the universe. It helps guide where to focus our efforts in exploring exoplanets and what conditions might be necessary to sustain life. As we gather more data from distant planets, we move closer to answering one of humanity's oldest and most profound questions. Are we alone in the universe? When scientists embark on the search for exoplanets that could potentially harbor life, they consider several crucial factors that make these distant worlds appealing. One of the most important considerations is the planet's location within what is known as the habitable zone, or the Goldilocks zone, around a star. This region is neither too hot nor too cold, allowing for the presence of liquid water, which is a fundamental requirement for life as we know it. If a planet lies within this zone, it becomes a prime candidate for further investigation. The planet's composition is another vital factor. Rocky planets, like Earth and Mars, are particularly intriguing because they have solid surfaces and atmospheres that might support living organisms. Gas giants, on the other hand, are less likely to be suitable for life exploration due to their lack of a solid surface and their extreme atmospheric conditions, which would be inhospitable to human life. A planet's atmosphere, however, could enhance its habitability. An atmosphere can shield the surface from harmful space radiation, regulate the planet's temperature, and even contribute the necessary chemical elements for life. Understanding a planet's atmosphere is crucial in determining whether it could sustain life. Scientists employ advanced techniques such as spectroscopy to analyze the atmospheres of exoplanets. By studying the light emitted by a star as it passes through a planet's atmosphere, they can detect specific gases, such as oxygen or methane, that might suggest biological processes. The presence of these gases could hint at the existence of life, or at least conditions suitable for it. Another key factor is the planet's proximity to Earth. Planets located closer to our solar system are more accessible for exploration, as current technology allows for missions to these distant worlds. A planet's distance from Earth is important not only for observation, but also for any potential future human missions. If a planet is too far away, the logistics of sending spacecraft to study it in person become increasingly difficult. The closer the planet is to our solar system, the more feasible it becomes to send probes or even human missions to gather more data. The combination of a planet being in the habitable zone, having a rocky composition, possessing a suitable atmosphere, and being relatively close to Earth makes certain exoplanets especially enticing for exploration. These factors fuel our fascination with the cosmos and our curiosity about what lies beyond our own planet. However, the quest to sustain human life on exoplanets involves more than just finding the right planet. It also requires the development of advanced space travel technologies capable of covering vast distances. The journey to even the nearest exoplanets would take many years, perhaps even decades, using current spacecraft propulsion methods. This challenge has led scientists to explore cutting-edge propulsion systems that could potentially allow spacecraft to travel at a significant fraction of the speed of light. Furthermore, life support systems must be engineered to ensure the safety and survival of humans on long-duration space missions. In summary, exploring the possibility of human life on exoplanets is an exciting yet daunting challenge. It demands a deep understanding of planetary science, advanced technology, and a willingness to push the boundaries of what is possible. As research continues and technology evolves, we edge closer to answering one of humanity's most profound questions. Could there be life on other planets? And can we one day become part of that cosmic story? When humanity eventually sets its sights on reaching an exoplanet, the journey will not only be an awe-inspiring technological feat, but also a deep testament to human ingenuity. The challenges we face will span not just the physical distance between our home planet and distant stars, but also the scientific, environmental, and psychological barriers that will shape our exploration. To settle on an exoplanet, developing sustainable living environments will be of paramount importance. This means creating habitats that can endure the harsh conditions of a foreign world, possibly with no access to Earth's resources. One approach might involve using local materials to construct shelter and infrastructure, relying on the planet's own elements instead of bringing everything from Earth. Agricultural systems would need to be specifically designed to thrive in the alien surroundings. Some have suggested that terraforming, the process of transforming a planet's environment to resemble Earth's, could be a key method. Terraforming would involve vast, complex changes to the atmosphere, temperature, and even the surface of the exoplanet in an attempt to make it more suitable for human life. The creativity and careful planning required for these steps would unlock incredible possibilities for the future of humanity, allowing us to one day become an interstellar species. However, the road to an exoplanet will not be easy. One of the most significant obstacles is the immense distance that separates us from the stars. Exoplanets, by definition, exist outside our solar system, often light years away. A light year, the distance light travels in a year, is roughly 5.88 trillion miles, 9.46 trillion kilometers. To put this into perspective, even with our fastest spacecraft, it could take decades or even centuries to reach a nearby exoplanet. One solution lies in developing much faster propulsion systems, technology that might enable travel at a fraction of the time it would take with current spacecraft. Such a system would need to harness enormous amounts of energy and be far more efficient than anything in use today. Another significant challenge involves the well-being of astronauts during the long journey. Astronauts would be confined to a spacecraft for years, possibly decades, and maintaining their health and morale will be crucial. Life support systems would need to supply essential resources, air, food, and water, over extended periods of time. These systems would need to be self-sustaining, recycling resources as efficiently as possible, and protecting the crew from the potentially harmful effects of microgravity and isolation. Physical health is one thing, but psychological health presents an even greater hurdle. Long-term isolation and confinement with limited social interaction would require comprehensive support systems designed to maintain mental and emotional well-being. One of the most pressing concerns in space travel is radiation. Outside the protective bubble of Earth's atmosphere, astronauts are exposed to intense cosmic radiation, which increases the risk of cancer and other long-term health issues. To mitigate this, spacecraft may need to incorporate advanced radiation shielding, possibly utilizing the ship's structure itself to create safe zones for the crew. These innovations would have to be both effective and lightweight, as carrying excessive materials on such a journey could increase the spacecraft's weight, making travel even more difficult. Assuming that a suitable exoplanet can be reached, the next step is to explore its surface, an endeavor that is fraught with uncertainty. Exoplanetary climates vary wildly depending on several factors, the most significant being the planet's location relative to its host star. This concept of the habitable zone, also known as the Goldilocks zone, refers to the area around a star where temperatures are just right for liquid water to exist, a key ingredient for life as we know it. If a planet is too close to its star, the heat will make it uninhabitable, while one that is too far may freeze over. Only planets situated within this zone offer the best chance of sustaining life. But even planets within the habitable zone are far from identical. For instance, the composition of a planet's atmosphere plays a massive role in shaping its surface conditions. Some exoplanets have thick atmospheres filled with gases like carbon dioxide, which trap heat through the greenhouse effect. This could create dangerously high surface temperatures. For example, WASP-121b, a particularly extreme exoplanet, has an atmosphere so dense that it may rain molten metal. Such conditions contrast sharply with Earth's balanced atmosphere of nitrogen and oxygen, highlighting how diverse and challenging these environments could be. Geological activity also influences the climate of an exoplanet. Active volcanoes, tectonic movements, and even the presence of magnetic fields can all shape the atmosphere over time. Some exoplanets may have entirely static climates, where conditions remain relatively constant, while others may experience rapid and unpredictable changes due to volcanic eruptions or seismic shifts. The potential to study these different geophysical processes is one of the most fascinating aspects of exoplanet research. In addition to atmospheric composition and geological activity, the size and density of an exoplanet also play a crucial role in its climate. Larger planets are able to retain thicker atmospheres and exert a stronger gravitational pull, which can affect how heat is distributed across the surface. Conversely, smaller planets may struggle to hold on to their atmosphere, resulting in stark temperature fluctuations and potentially hostile conditions. As scientists continue to explore the vast diversity of exoplanets, they uncover new possibilities for life beyond Earth. Some exoplanets may even possess seasonal cycles, much like Earth's. These changes in temperature, light, and precipitation would influence the development of life on such planets. A significant axial tilt, for instance, could result in more extreme seasonal variations, creating lush growth during one season and harsh conditions in another. Life on these planets would need to adapt to these cycles, evolving strategies to survive during times of abundance and scarcity. In fact, exoplanets with more extreme seasonal changes may give rise to some truly unique survival tactics. Imagine a world with an elongated orbit, where the planet experiences intense heat and light during its closest approach to its star, followed by frigid temperatures as it moves farther away. This cycle could create ecosystems with rapidly evolving life forms capable of enduring extreme conditions. Life on such a world might thrive during short bursts of warmth and light, then enter dormancy during colder periods. The ability to adapt quickly could be essential to survival. The atmosphere of an exoplanet would also play a role in shaping these seasonal patterns. A planet with a thick, greenhouse-rich atmosphere might experience milder seasonal changes, promoting a more stable ecosystem throughout the year. In contrast, a planet with a thin atmosphere could lead to rapid temperature fluctuations that force life to evolve remarkable flexibility and resilience. This interplay between the atmosphere, seasons, and ecosystems could create dynamic, ever-changing environments. The study of weather on exoplanets is an entirely new frontier for scientists. Earth's weather models, honed over centuries of observation, are based on a relatively stable and predictable system. However, exoplanet weather could be wildly different, shaped by unique atmospheric conditions, extreme temperatures, and even unfamiliar chemical compositions. Some exoplanets, for instance, experience temperatures that reach thousands of degrees, possibly giving rise to bizarre weather phenomena, such as clouds made of heavy metals. One particularly fascinating type of exoplanet is the tidally locked planet. On these worlds, one side always faces the star, while the other remains in perpetual darkness. This extreme difference in temperature between the two hemispheres could create intense winds, storms, and localized weather patterns that defy our current understanding of meteorology. These planets may also experience entirely new forms of precipitation, further challenging what we know about weather systems. As we venture deeper into the cosmos and discover more about the incredible variety of exoplanets, we find ourselves facing questions that have never been asked before. How will life adapt to environments where seasons are extreme and unpredictable? How will we harness the resources of distant worlds to create sustainable habitats for human life? And perhaps most importantly, what new forms of life might we encounter in these far-flung corners of the universe? These questions are only the beginning, and as technology advances, humanity's exploration of exoplanets will unfold in ways we can only begin to imagine. Exoplanets, those distant worlds orbiting stars far beyond our solar system, continue to reveal their mysteries to scientists in fascinating and unexpected ways. As we venture deeper into the study of these alien planets, One of the most intriguing aspects is their atmospheres, which often differ drastically from our own. Some of these exoplanets harbor atmospheres filled with gases that are unknown to Earth's atmosphere. For instance, these otherworldly atmospheres can contain compounds such as hydrogen, helium, and various metallic or acidic vapors. These substances, which might seem strange or even dangerous to us, play a pivotal role in shaping the weather systems on these distant worlds. When we attempt to model the weather on these far-off planets, we find ourselves venturing into uncharted territory. To predict how these atmospheres behave, we must take into account the intricate chemical interactions that occur in conditions utterly unlike those on Earth. This could lead to the formation of weather phenomena we cannot even begin to imagine, such as clouds made not of water vapor, but of vaporized metals. The idea that clouds could be composed of metallic particles instead of water droplets challenges our basic understanding of weather itself. The exploration of these foreign weather systems opens up an exciting new frontier in meteorology, pushing the boundaries of what we know about planetary atmospheres. As new data streams in from powerful telescopes and upcoming space missions, scientists continue to refine their models, constantly adjusting and adapting their predictions. This ongoing process not only enriches the field of comparative meteorology, but also raises profound philosophical questions about the universality of weather systems. Could the fundamental principles governing weather on Earth be applicable across the cosmos? Or are we encountering entirely unique phenomena in distant star systems? This exploration drives us to rethink what we know about the atmospheres of planets far beyond our blue home. It forces us to confront the possibility that life elsewhere in the universe might not be subject to the same atmospheric conditions that we experience here, opening the door to entirely new ways of understanding and studying planetary environments. One of the most groundbreaking techniques used to discover exoplanets is the transit method. This approach involves observing the subtle dimming of a star's light as a planet passes directly in front of it from our perspective on Earth. This event, known as a transit, may seem simple in concept, but detecting it is anything but. To capture such small changes in brightness, astronomers employ highly sophisticated methods. One key technique involves continuously monitoring the brightness of stars over time, collecting data that creates a light curve, a graph that tracks variations in brightness. When a planet crosses in front of its star, it causes a tiny but noticeable dip in the star's brightness. By analyzing the depth and duration of this dip, astronomers can infer crucial details about the planet, such as its size and the shape of its orbit. A larger planet, for example, will block more light and cause a more pronounced drop in brightness than a smaller planet. The precision required to detect these minuscule changes in light is immense. The fluctuations caused by transiting planets are often smaller than 1%, making them difficult to discern. To achieve this level of accuracy, astronomers rely on advanced photometry, the art of measuring light intensity with extreme precision. With space telescopes like Kepler and TESS, which are equipped with sensitive instruments, astronomers can detect these faint signals amid the cosmic noise. These telescopes have revolutionized our ability to spot transiting exoplanets by simultaneously observing multiple stars, thereby increasing the likelihood of detecting a planet's transit. However, detection is just the first step. After spotting a potential transit, astronomers conduct follow-up observations to confirm the existence of the exoplanet and gather more data. These follow-up observations often include searching for additional transits, which can help determine a planet's orbital period. Other techniques, such as measuring the planet's radial velocity, also play an essential role in verifying its mass and size. Each new observation helps build a more complete picture of the exoplanetary system, further deepening our understanding of the complex and diverse worlds beyond our own. Alongside the transit method, the radial velocity technique has been instrumental in expanding our knowledge of exoplanets, particularly when it comes to measuring their masses. This method is based on the principle of Doppler shift, which describes how the frequency of light changes due to the motion of an object. When a planet orbits a star, its gravitational influence causes the star to wobble ever so slightly. This subtle movement shifts the star's light spectrum, allowing astronomers to detect changes in the star's velocity, both towards and away from us. By measuring these shifts, astronomers can infer not only the presence of a planet, but also its mass. The greater the mass of the planet, the more significant its gravitational pull on the star, resulting in a more noticeable radial velocity signal. Even though the planet itself may remain invisible, this technique provides a valuable window into the planet's properties. It also offers crucial insights into how planets form and evolve over time. Early in the search for exoplanets, astronomers found that many of the first detected planets were massive, gaseous giants, similar to Jupiter. These findings challenged our initial assumptions and expanded our understanding of what kinds of planets could exist. However, as technology advanced, astronomers began to detect smaller rocky planets as well, broadening the range of planetary types that we could study. The ability to detect these smaller worlds opens up new possibilities for studying planets that might harbor life. The radial velocity method has thus transformed our understanding of exoplanetary systems, providing a clearer picture of the wide range of planetary masses in our galaxy. This technique is not only revealing the diverse variety of exoplanets, but also giving us insight into how these planets interact with their stars, how they might form, and how they evolve over time. In recent years, the study of exoplanet atmospheres has emerged as one of the most exciting areas of research. Determining the composition of an exoplanet's atmosphere offers us a glimpse into the conditions on these distant worlds. However, this task is far from simple. One of the most widely used techniques for studying exoplanet atmospheres is transmission spectroscopy. This method involves observing the starlight that passes through a planet's atmosphere during a transit. By analyzing the spectrum of this light, astronomers can detect the chemical elements and compounds present in the planet's atmosphere. However, transmission spectroscopy has its limitations. For one, it works best for larger exoplanets that block a significant amount of light. Smaller planets, especially those that could potentially harbor life, are often much harder to study because they block less light, making their atmospheres more difficult to detect. Additionally, the brightness of a star plays a significant role. Systems with bright stars are easier to study, but many smaller, dimmer planets are harder to detect, hidden in the glare of their parent stars. Another challenge lies in the composition of the atmosphere itself. Many exoplanets possess thin or chemically complex atmospheres, making them difficult to study. In some cases, clouds or hazes obscure our view of the planet's atmosphere, complicating the interpretation of the data. Even when astronomers do manage to obtain useful data, the signals they receive can be faint, often drowned out by the overwhelming light of the parent star. Sorting through this noise requires highly sophisticated models and sometimes speculative guesswork. Moreover, current telescopes and instruments, though advanced, are not without their limitations. Earth-based telescopes, for example, are hindered by atmospheric distortions, which can blur the light signals coming from distant stars. Weather conditions and pollution further complicate observations made from the surface of our planet. While space telescopes provide a clearer view, they too have limits in terms of their resolution and sensitivity. Despite these challenges, progress is being made. Upcoming space telescopes designed specifically for the task of studying exoplanet atmospheres promise to push the boundaries of what we can learn about these distant worlds. As technology advances, we inch closer to answering some of the most profound questions about the nature of planets, atmospheres, and potentially even life beyond our solar system. Each new discovery is a step toward understanding the vast and varied universe that surrounds us, and it drives us to question just how many more unknown worlds are waiting to be discovered. The vast distances in space introduce a significant delay in our ability to discover and study distant worlds, a delay known as the light-time travel problem. The light that reaches us from far-off planets carrying vital data can take years, sometimes even centuries, to arrive. This means that while we might detect an exoplanet today, we are in fact observing it as it was eons ago. These light years of distance create a layer of time between observation and reality, forcing scientists to study the past state of these distant worlds. As our observational technologies and techniques improve, the challenge remains. It is not enough merely to detect the existence of an exoplanet. We must delve into its atmosphere. Understanding the intricate relationships between the elements of an atmosphere, the way they interact, and how they influence the planet's potential for habitability is a monumental task. This complexity is not easily overcome, but the pursuit of such knowledge drives astronomers forward into the unknown. Despite these monumental challenges, the quest for exoplanet atmospheres continues to captivate and inspire those of us who seek to understand what lies beyond our solar system. The journey of understanding exoplanets begins with a structured process, a meticulous system to categorize and name these far-off worlds. When a new exoplanet is discovered, it is classified based on its key features, its size, mass, and the nature of its orbit around its parent star. This process allows scientists to place the planet into one of several broad categories: gas giants, rocky planets, or icy worlds. Such distinctions help create a more organized map of the cosmos, like making it easier to compare these new discoveries with the planets of our own solar system. Naming an exoplanet is no less structured, and this process follows a fascinating set of guidelines set by the International Astronomical Union, IAU. When an exoplanet is first identified, it is given a temporary designation derived from the name of its parent star. Often, this designation is followed by a letter to indicate its place in the order of discovery. For instance, a star labeled HD 29458 might have its first discovered planet named HD 29458b, where the B signifies that this was the first planet detected orbiting that star. Subsequent discoveries around the same star are then labeled HD 29458c, HD 29458d, and so on. But the naming process doesn't stop with the scientific community. The IAU often opens up the naming process to the public, inviting enthusiasts and ordinary citizens to suggest and vote on names for newly discovered exoplanets and their host stars. This approach encourages a sense of global participation and fosters a connection between the public and the stars themselves. The names chosen can reflect elements of mythology, literature, culture, or even characteristics of the planet that are deemed significant or poetic. In this way, the process of naming becomes more than just an administrative task. It becomes a bridge between the cold analytical world of science and the rich tapestry of human creativity and history. For example, the planet HD 29458b has been named Osiris, after the ancient Egyptian god of the afterlife. This is not only a nod to the planet's striking features, its atmosphere, which scientists believe may be crucial in studying atmospheric loss, but also a way to connect human culture and mythology with modern astronomical research. Naming planets after gods, legends, and ancient figures gives them a story and a meaning, turning these distant, lifeless rocks into something more profound. It's as if the mythologies and ancient tales of humankind are woven into the fabric of the universe itself, lending a sense of continuity between our past and our future in the stars. The naming process itself is a collaborative effort that unites people from all over the world. Different cultures contribute their perspectives, ideas, and interpretations, and in doing so, they give these planets names that are rich in cultural significance. This global collaboration underscores humanity's collective curiosity, its thirst for knowledge, and its desire to understand the cosmos. In this way, naming an exoplanet becomes an act of cultural celebration, a recognition of our shared exploration of the universe. In many ways, the names we assign these distant worlds are more than just labels. They are an invitation to engage with the cosmos on a more personal level. They serve to spark the imagination, encourage curiosity, and make the abstract more tangible. When people are involved in the naming of exoplanets, it fosters an emotional connection to the science behind them. Rather than simply reading about planets with names like HD 29458b or Kepler 22b, individuals have the opportunity to contribute to the creation of a name that holds meaning and significance for them. This process transforms the discovery of new planets into something more immediate, real, and relatable. The involvement of the public in naming exoplanets also provides a valuable platform for educational outreach. Schools, libraries, and community organizations can use these opportunities to spark interest in astronomy and science, especially among young people. The chance to name a planet can inspire a sense of ownership and excitement, encouraging individuals to learn more about the science that makes such discoveries possible. This engagement can create a ripple effect that enhances science literacy, encouraging individuals to explore more about the universe and share that knowledge with others. As we move forward in our exploration of the cosmos, the names we give to these exoplanets will continue to be a reflection of our collective curiosity and imagination. These names are not just identifiers, they are symbols of our desire to understand the universe, to find our place within it, and to connect with something far larger than ourselves. Beyond the naming process, the life cycle of a star is a key factor in determining the potential habitability of its orbiting planets. Stars, born from massive clouds of gas and dust, follow an evolutionary path that dictates not only their brightness and temperature, but also the conditions of the planets that orbit them. The life cycle of a star is often divided into several stages: the main sequence, the red giant phase, and the final stages, which can culminate in a white dwarf or a supernova. Each of these stages dramatically impacts the environment around the star and any planets within its reach. During the main sequence phase, a star is stable, shining steadily and providing a constant source of energy. This is the most favorable period for the existence of life, especially if the planet is located within the star's habitable zone, the region where conditions allow liquid water to exist. For smaller stars, such as red dwarfs, this phase can last for billions of years, providing ample time for life to evolve and thrive. In contrast, more massive stars burn through their fuel much more quickly, living for only a few million years, a blink of an eye in cosmic terms, offering a much shorter window for life to take hold. When a star exhausts its fuel and expands into a red giant, the conditions around its planets change drastically. The star's outer layers swell and cool, and the heat from the expanding star can strip away the atmospheres of nearby planets, boiling away oceans, or even causing the planet to become entirely inhospitable. For example, if Earth were to orbit the Sun during this phase, it would experience devastating conditions that would likely render it uninhabitable. After this stage, the star enters the final stages of its life, eventually transforming into a white dwarf, where its energy output dramatically diminishes. At this point, the conditions for life on nearby planets become even more hostile. The life cycle of a star is a key factor in determining the habitability of its planets. Understanding the stages of stellar evolution gives astronomers insight into how long a planet might have to support life, as well as what conditions might be present at different points in a star's life. As we study dying stars and their transformations, we gain a window into the future of exoplanets. These observations not only inform our understanding of the types of environments in which life could thrive, but also help us predict what may happen to Earth and our own solar system in the distant future. The study of dying stars unveils profound clues about the very building blocks of the universe. As these celestial giants burn through their nuclear fuel, they begin to shed their outer layers, ejecting vast amounts of material into the surrounding space. This process enriches the interstellar medium with heavier elements, some of which are destined to become part of new stars and planets. These recycled elements play a crucial role in the formation of future worlds, offering us a unique opportunity to trace the cosmic journey of matter across time. By understanding these cycles, scientists gain insights into how the composition of exoplanets evolves and how the conditions for life may change over millions, if not billions, of years. Focusing on the lives of older stars allows astronomers to speculate about the future of exoplanets in nearby systems. When studying the changes in dying stars and their effects on surrounding planets, we can make informed comparisons to similar processes that might be happening in other distant star systems. This rich tapestry of cosmic evolution not only helps us comprehend the life cycles of stars, but also reveals the ultimate fate of the planets that orbit them. In this grand cosmic drama, the fate of a planet is often intricately tied to the lifespan of its parent star. The longevity of a star plays a critical role in shaping the environments of the planets that orbit it, particularly when it comes to their atmospheres. While a star's life cycle spans billions of years, different types of stars experience vastly different lifespans. For instance, a small star like a red dwarf can burn steadily for tens of billions of years, while a massive star may only shine for a few million years before exploding in a supernova. This immense difference in lifespan has direct implications for how long a planet can sustain a stable atmosphere, which is vital for supporting life. During the main sequence phase of a star's life, it provides a relatively steady flow of energy, creating a stable environment for any planets that orbit it. This stability allows a planet's atmosphere to evolve over time, giving it the opportunity to nurture complex chemical and biological processes. For planets orbiting stars with longer lifespans, like our Sun, there is ample time for life to potentially emerge, as biochemical processes can unfold gradually. On the other hand, planets that orbit stars with shorter life expectancies may face rapidly changing conditions that could hinder the development of stable atmospheres and, by extension, the emergence of life as we understand it. As stars exhaust their nuclear fuel, they undergo profound transformations that dramatically alter their energy output. Our Sun, for instance, will eventually swell into a red giant, shedding its outer layers in the process. These changes will have profound effects on the planets that orbit it, potentially stripping away their atmospheres entirely or drastically altering their chemical compositions. If a planet's atmosphere is lost, the conditions on its surface may become inhospitable, making life impossible. This stark reality emphasizes the importance of a star's type and lifespan in determining the long-term habitability of any orbiting planets. The stability of a star's energy output also plays a key role in maintaining a balance between heat and cold, which is crucial for sustaining liquid water, the essential ingredient for life. When considering the long-term habitability of a planet's atmosphere, the lifespan of its parent star is not merely an abstract detail. It holds profound implications for the planet's climate, its atmospheric development, and, most importantly, its potential to support life. As we explore the vast expanse of the cosmos and encounter countless exoplanets, two fundamental concepts come to the forefront: habitability and the actual presence of life. Habitability refers to the conditions that would allow life to potentially develop, while the presence of life refers to the actual existence of living organisms. These two concepts, though related, are distinct and have important implications for the search for life beyond Earth. For a planet to be considered habitable, it must possess a stable supply of key resources, such as water, a suitable atmosphere rich in essential gases, and the right temperature range to allow liquid water to exist. These conditions create a nurturing environment in which life could, in theory, take root. However, meeting these criteria does not guarantee the emergence of life. Life requires more than just the right resources. It demands complex biological processes that have evolved over time. The geological and climatic stability of a planet is also critical. Planets that can maintain stable environments over long periods are more likely to support life, as this stability allows for the chemical processes necessary for life to unfold. Even in the most stable environments, however, life is not a foregone conclusion. The emergence of life depends on a multitude of factors, many of which remain shrouded in mystery. Evolutionary advantages, historical contingencies, and a host of other factors play a crucial role in determining whether life will take hold. In addition, there are certain chemical and physical dynamics that influence whether the ingredients for life are enough to spark its formation. For instance, a planet may possess all the necessary ingredients for life, but still lack the catalytic processes required to kickstart life, such as lightning or volcanic activity. In the quest to understand the potential habitability of exoplanets, scientists have turned to laboratory simulations that replicate the extreme conditions found in space. By recreating the temperature, pressure, and chemical composition of distant exoplanets, researchers can study how life, or at least the conditions for life, might exist in those environments. These experiments are crucial because exoplanets are often light years away and direct observation is limited. By simulating the atmospheres of these planets, scientists can investigate how organic molecules behave under extreme conditions, helping them to understand the potential for complex chemistry and the formation of life. These simulations are not carried out in isolation. They often involve collaborations across multiple disciplines, including astronomy, chemistry, and biology. Researchers also study life forms on Earth that thrive in extreme environments, such as deep sea vents or polar ice caps, because these organisms provide valuable insights into how life might adapt to harsh conditions on other planets. This multidisciplinary approach has proven to be invaluable in advancing our understanding of what it takes for life to emerge in the universe. Ultimately, these lab simulations provide critical insights into the potential habitability of distant worlds. By understanding the limits of life on Earth, scientists can refine their search for habitable planets and move closer to answering the age-old question of whether we are truly alone in the universe. The knowledge gained from these efforts not only enhances our understanding of exoplanets, but also deepens our appreciation for the complexity and resilience of life as we know it. The potential discovery of intelligent extraterrestrial life would present humanity with profound ethical challenges that touch upon our values, responsibilities, and our understanding of our place in the cosmos. The first question we must grapple with is how we would interact with such beings. Would we treat them as equals, or would we impose our own values and behaviors upon them? This fundamental dilemma challenges our notions of respect, coexistence, and the ethics of exploration, urging us to consider the implications of imposing our worldview on societies that may be entirely different from our own. Another pressing concern is the challenge of communication. How would we convey our intentions to extraterrestrial beings? Would we run the risk of misunderstanding or misinterpretation leading to conflict rather than collaboration? This dilemma emphasizes the importance of thoughtful and respectful communication, avoiding any appearance of aggression or superiority. The ability to bridge the communication gap may be critical in fostering peaceful relationships based on mutual understanding and respect. There is also the question of the potential risks associated with contact. If we discover intelligent life, what responsibilities do we have to protect both our own planet and theirs? History has shown us that encounters between different cultures on Earth often result in exploitation and harm. We must ask ourselves whether humanity has the moral capacity to approach such a monumental discovery with the caution and responsibility it demands. Each step we take in this endeavor could have far-reaching consequences, not just for us, but for any alien life forms we may encounter. The discovery of intelligent extraterrestrial life is not just a scientific milestone. It is a philosophical and ethical crossroads that challenges humanity to reflect on its place in the cosmos and to approach the universe with humility, respect, and a deep sense of responsibility. When we contemplate the possibility of discovering intelligent extraterrestrial life, we are not merely engaging with a scientific breakthrough, but also embarking on a profound journey that challenges the core of our identity and worldview. The implications of such a discovery extend far beyond the boundaries of space exploration, forcing us to reconsider fundamental aspects of our existence. Could the existence of intelligent beings elsewhere challenge our deepest held religious beliefs and philosophical perspectives? Could it reshape the very notion of what it means to be human? The prospect of extraterrestrial life forces us to confront profound questions about life, intelligence, and our place in the cosmos, questions that could redefine humanity's role in the grand narrative of the universe. This reflection is not just an abstract intellectual exercise, but a crucial ethical inquiry that compels us to examine the essence of who we are as a species. If intelligent extraterrestrial life were discovered, the ethical dimensions of our response would become a matter of great concern. How would we treat these new forms of intelligence? Would we approach them with empathy and respect, or with fear and hostility? These questions are not speculative. They strike at the heart of our moral compass and our understanding of responsibility. It would force us to reflect on the very principles that guide our interactions with each other on Earth, principles of kindness, respect, and justice, while considering their application to an entirely new realm of existence. For decades, science fiction has played an instrumental role in shaping both public perception and scientific curiosity surrounding the search for exoplanets and the possibility of life beyond Earth. Through the captivating tales of distant worlds, alien civilizations, and interstellar travel, fiction has sparked the imagination of countless people, propelling them to think beyond the confines of our planet. It is no coincidence that films, books, and television series such as Star Trek, The Martian, and Contact have captivated audiences, weaving complex ideas about space, planetary systems, and the conditions required for life into accessible and engaging narratives. These fictional works do more than entertain. They educate. They introduce viewers and readers to scientific concepts that would otherwise remain abstract or inaccessible. For example, the concept of the Goldilocks zone, where planets orbit their stars at just the right distance to allow liquid water and possibly life, is made tangible through science fiction. Such stories have not only fired up public enthusiasm for space exploration, but have also played a pivotal role in transforming abstract scientific theories into possibilities that feel real and within our grasp. Moreover, science fiction often mirrors the very real scientific endeavors that are unfolding today. As astronomers discover and catalog exoplanets, planets that orbit stars outside our solar system, the public's curiosity grows. The excitement generated by stories of habitable worlds filled with potential life forms has turned what was once an academic pursuit into a thrilling human adventure. With each new discovery, whether it involves the detection of Earth-like planets or the discovery of potential biosignatures, the excitement around exoplanets grows, feeding both scientific inquiry and popular imagination. The boundaries between science fiction and science itself are becoming increasingly blurred. In many ways, these fictional worlds do not simply reflect our hopes and aspirations. They help guide the conversation about humanity's place in the cosmos. As the search for exoplanets continues, the creative narratives of science fiction help us think through the social, ethical, and existential implications of our discoveries. The idea of establishing colonies on distant worlds, for instance, offers a lens through which we examine the future of human civilization. These tales of space colonization often revolve around themes of escaping a ravaged Earth, whether due to environmental catastrophe, war, or overpopulation. In these stories, humanity often finds itself on distant planets that closely mirror Earth, offering the possibility of a fresh start, a new frontier to explore. Yet, these colonization narratives are not without their dark sides. Many of them explore the potential risks and challenges that come with living on alien worlds, whether it's surviving in harsh environments, navigating deadly ecosystems, or dealing with resource scarcity. These stories underscore humanity's resilience and adaptability. In many ways, they serve as both cautionary tales and blueprints for what might lie ahead. A particularly captivating element in the science fiction narrative surrounding exoplanets is the theme of intelligent extraterrestrial life. The prospect of first contact with an alien civilization invites us to grapple with profound questions about communication, cooperation, and even ethics. What would it mean to meet another species whose way of life is entirely foreign to us? Would we be able to communicate with them, or would the very act of contact require new methods of understanding and interaction? The diversity of imagined alien cultures in these stories prompts us to think deeply about the nature of life itself and our assumptions about intelligence, consciousness, and morality. In addition to these visionary scenarios, some of the most compelling stories explore the harsh realities of life on exoplanets. These worlds, often portrayed as hostile environments with extreme climates and bizarre ecosystems, provide a canvas for exploring the limits of human ingenuity. Whether it's surviving on gas giants with thick jungles or enduring the freezing tundras of icy worlds, these extreme conditions highlight the strength and resourcefulness of humanity in the face of adversity. Such narratives force us to reflect on our ability to adapt and thrive in unfamiliar and challenging circumstances. Time travel and alternate realities also make their way into the discourse surrounding exoplanets. Some science fiction narratives propose that these distant worlds could serve as gateways to other times or dimensions, enabling thrilling adventures that defy the laws of space and time. Characters who venture into these alternate realities navigate not only the vastness of space, but also the very fabric of time itself, creating an exciting exploration of fate, choice, and consequence. These stories invite us to reconsider the very nature of reality, suggesting that perhaps the universe holds even more mysteries than we can fathom. Artistic representations of exoplanets offer yet another layer to this complex dialogue. The creative community has long been fascinated by the idea of distant worlds, and with each new scientific discovery of exoplanets, artists eagerly attempt to imagine what these planets might look like. These visual interpretations are not merely whimsical illustrations, they reflect our collective hopes and fears. Some portray lush, Earth-like environments teeming with life, symbolizing hope and the possibility of finding new forms of life that might inspire cooperation and mutual understanding. Others depict barren, hostile landscapes, mirroring our anxieties about the future of our own planet, particularly in the face of climate change, resource depletion, and unchecked technological advancement. These artistic representations not only allow us to explore the beauty of alien worlds, but also serve as poignant reminders of the fragility of life itself, urging us to consider the choices we make on Earth. Ultimately, the discovery of exoplanets and the possibility of extraterrestrial life confronts us with a range of profound philosophical, ethical, and existential questions. As we venture further into the cosmos, we find ourselves at a crossroads, one that challenges our understanding of life, intelligence, and our place in the universe. Through the lens of science fiction, we not only imagine what lies beyond the stars, but also engage in a deeper conversation about who we are as a species and what we are capable of becoming. The exploration of exoplanets is not merely a scientific endeavor, it is a mirror held up to our own humanity, urging us to reflect on our past, our present, and the future we are shaping. Moreover, these artistic portrayals often venture into deep philosophical realms, raising profound questions about humanity's role in the vast expanse of the cosmos. They invite us to reflect on our place in the universe, pushing us to ask, are we truly alone in the cosmos? What would it mean for our species, our identities, and our values if we were to make contact with extraterrestrial civilizations? These artistic expressions, while inspired by the discoveries of distant exoplanets, offer more than just a visual interpretation of scientific findings. They spark dialogues that extend well beyond the confines of astronomy. They delve into ethics, existentialism, and even our very understanding of consciousness, proposing new perspectives on what it means to be human. In this way, the art surrounding exoplanets serves not just as an aesthetic endeavor, but as a bridge between the empirical, scientific world and the complex, emotional, philosophical framework through which we navigate life. These creative expressions do more than just captivate our imagination. They help us dream of possibilities while reminding us to remain grounded in the realities of our existence. They form an essential part of the ongoing dialogue about humanity's future in the cosmos, adding a deeply human dimension to the scientific exploration of distant worlds. Among the stars, Kepler-186f stands out as a particularly fascinating exoplanet, one that has captivated the attention of scientists and the public alike for several compelling reasons. Discovered by NASA's Kepler Space Telescope in 2014, Kepler-186f has earned the distinction of being the most Earth-like planet discovered up to that point in time. Its most notable feature is its location in the so-called habitable zone of its star, a region where the conditions are just right for liquid water to exist, an essential ingredient for life as we understand it. This planet orbits a red dwarf star, a type of star that is cooler and smaller than our Sun. While red dwarfs are abundant in the Milky Way, their faintness means that the planets orbiting them experience very different conditions compared to those orbiting larger stars. Kepler-186f, for example, receives about 1/3 of the energy that Earth receives from the Sun. Despite this, its temperature may still be conducive to the presence of liquid water, if the planet possesses a suitable atmosphere. This raises the tantalizing possibility that life could exist on this distant world, especially if conditions are similar to those on Earth. Kepler-186f's size is another intriguing aspect. It is approximately 1.1 times the size of Earth, which classifies it as a super-Earth. Its slightly larger size hints that it may have a rocky surface, which in turn suggests that it could support a climate similar to our own, again, provided it has the necessary atmosphere. This exciting possibility fuels our imagination and leads us to wonder what kinds of life forms might exist on this distant planet. Could it be home to life that is similar to, or even more advanced than, life on Earth? The discovery of Kepler 186f opens the door to profound questions about our place in the universe. As we explore these distant worlds, we not only gain insights into the incredible diversity of planetary systems, but we also deepen our understanding of the potential for life beyond our own planet. Every new discovery prompts us to ask, just how unique is our Earth in the vast cosmos? Could there be other planets out there, distant cousins to our own, waiting to be discovered? WASP-121b, another exoplanet, presents an entirely different kind of fascination. Located roughly 800 light-years away from Earth, WASP-121b is a gas giant, a hot Jupiter in scientific terms. Similar in size to Jupiter, it orbits its star at an extraordinarily close distance, resulting in extreme environmental conditions. The planet's daytime temperatures soar to over 2,500 degrees Celsius, hot enough to vaporize metals like iron and magnesium. This has created a truly unique and extreme atmosphere, one that is unlike anything we encounter on Earth. One of the most intriguing aspects of WASP-121b is its weather systems. Unlike the familiar weather patterns we experience on Earth, rain, snow, and wind, WASP-121b experiences rain made of molten metals due to the planet's intense temperatures. The planet's extreme atmospheric pressure contributes to this phenomenon, essentially acting as a giant pressure cooker that drives the scorching weather. Winds whip across the planet at unimaginable speeds, contributing to dynamic and turbulent atmospheric conditions. Scientists are eager to study these phenomena as they offer insights into the processes that shape planetary atmospheres. Additionally, WASP-121b presents an unusual day-night temperature contrast. One side of the planet is constantly exposed to its star, while the other remains in eternal darkness. This stark division leads to dramatic atmospheric effects, including the rapid transfer of heat from the day side to the night side, which drives some of the fastest winds ever observed in planetary atmospheres. Winds can reach speeds of up to 2,500 kilometers per hour, remarkably high even by the standards of extreme weather phenomena on Earth. By studying these fluctuations in light and temperature, astronomers have detected various elements in WASP-121b's atmosphere, including water vapor and possibly even heavy metals. This ongoing research helps us expand our understanding of the diversity of planetary atmospheres in the universe, furthering our knowledge of exoplanetary weather systems. The discovery of WASP-121b paints a vivid picture of the extremes that exist in the cosmos. It serves as a reminder that the universe is full of strange, uncharted worlds that challenge our notions of what is possible. Each new discovery prompts us to ponder the mysteries that lie hidden among the stars. The exoplanet LHS 1140b is another discovery that has reshaped our understanding of potentially habitable worlds. Situated about 43 light-years away in the constellation of Sculptor, LHS 1140b has quickly captured the attention of scientists due to its intriguing characteristics. Like Kepler 186f, LHS 1140b is classified as a super-Earth, a rocky planet that is larger than Earth but smaller than Neptune. However, what sets LHS 1140b apart is its position within the habitable zone of its star, where conditions might be ideal for the presence of liquid water. What makes LHS 1140b particularly compelling is its substantial atmosphere, which scientists believe could contain the necessary elements for biological processes to take place. Its density suggests that the planet likely has a solid surface, and recent studies indicate that it may possess a thick layer of clouds capable of regulating temperature variations. This combination of a solid surface and a stable atmosphere challenges the traditional notion that only Earth-like planets are suitable for supporting life. In other words, the criteria for habitability are becoming more flexible, which suggests that the universe may be teeming with diverse environments in which life could emerge. Each of these exoplanet discoveries, Kepler 186f, WASP-121b, and LHS 1140b, invites us to explore not only the potential for life beyond Earth, but also to reconsider the very nature of life itself. As our understanding of these distant worlds expands, so too does our understanding of what is possible in the cosmos. The journey of exploring exoplanets, planets that orbit stars outside our solar system, has not only expanded our knowledge of the cosmos, but has also fundamentally shifted the way we approach the concept of habitability. A key example in this exploration is LHS 1140b, a world that orbits a red dwarf star. These stars are often overlooked in the broader search for life, yet they present unique opportunities and challenges. While red dwarfs are more stable than many other types of stars, their radiation can be harsh on nearby planets, potentially damaging their atmospheres or making them inhospitable. However, the long cold phase that characterizes red dwarfs provides planets like LHS 1140b with an extended period during which conditions may stabilize, offering a broader window of opportunity for life to develop. This discovery has prompted a critical rethinking in the scientific community about how we define habitability. It challenges the long-held assumption that only Earth-like conditions, such as proximity to a sun-like star, can foster life. Instead, it opens up new possibilities for life-supporting environments on planets that we may never have considered in the past. As a result, the search for extraterrestrial life is evolving, and we are learning that there may be many more potential candidates for life than we initially believed. In this context, LHS 1140b serves not just as a distant world of scientific interest, but as a vivid reminder of the extraordinary diversity within our galaxy. It encourages astronomers and researchers to broaden their search criteria, taking into account a wider range of planetary environments. As we continue to study exoplanets like LHS 1140b and others, we are only beginning to scratch the surface of what makes a world potentially habitable. Our expanding understanding is igniting new curiosity about life beyond Earth, fueling a global effort to explore the unknown. One of the key drivers of this shift in perspective is international collaboration. The study of exoplanets has become a truly global enterprise, uniting the brightest minds from across the world to pool resources, ideas, and technologies. Through international partnerships, scientists are tackling increasingly ambitious projects that push the boundaries of what we know about the distant planets orbiting stars light years away. These collaborations allow for the development and use of a variety of advanced tools, from space telescopes to ground-based observatories, enhancing our ability to study these planets in unprecedented detail. For example, while one country may host a ground-based telescope capable of high-precision imaging, another country might operate a space telescope tuned to capture different wavelengths of light. By combining the strengths of these diverse observatories, researchers can gather data from multiple perspectives, leading to a more comprehensive understanding of exoplanetary systems. This multidimensional approach not only enriches the quality of the data, but also provides a stronger validation for scientific findings, ensuring that our conclusions about distant planets are both reliable and accurate. Moreover, international collaborations extend beyond the realm of astronomy. They bring together experts from a range of scientific disciplines, including chemistry, geology, atmospheric science, and even astrobiology. This interdisciplinary approach enables researchers to analyze exoplanet atmospheres, interpret spectral data, and simulate planetary formation processes in ways that would be difficult to achieve within a single scientific field. Such teamwork results in a more robust and integrated framework for understanding how exoplanets form, evolve, and potentially support life. These collaborations also help foster a global scientific community, promoting the exchange of knowledge and ideas. They inspire innovation and motivate the next generation of astronomers, encouraging young researchers to engage in collaborative projects that ultimately lead to groundbreaking discoveries. By joining forces on large-scale missions, scientists can accelerate the pace of discovery and deepen our understanding of the complex and diverse worlds that lie beyond our solar system. One of the most exciting developments in exoplanet exploration is the array of current global projects. NASA's Transiting Exoplanet Survey Satellite, TESS, launched in 2018, represents a major step forward in identifying exoplanets. By focusing on nearby stars and observing the dimming of their light as planets pass in front of them, TESS is helping to pinpoint candidate planets that could later be studied in greater detail. Meanwhile, the European Space Agency's upcoming Plato mission, set to launch in the near future, promises to expand on the techniques pioneered by TESS, with the goal of discovering Earth-like planets orbiting stars similar to our Sun. On Earth, ground-based observatories are also making significant strides in exoplanet research. The Very Large Telescope in Chile, for instance, uses high-precision methods to directly image exoplanets and gather crucial data on their atmospheric composition. Similarly, the Keck Observatory in Hawaii employs adaptive optics to counteract atmospheric distortion, enabling astronomers to study the light from distant planets in remarkable detail. These advancements, combined with cutting-edge technology like the James Webb Space Telescope, which launched in late 2021, are pushing the boundaries of what we can learn about exoplanetary atmospheres. Webb's ability to analyze chemical signatures in the atmospheres of exoplanets offers new opportunities to detect signs of water, organic molecules, and even potential biosignatures that could hint at the presence of life. As these technological advancements unfold, the future of exoplanet exploration looks increasingly promising. Global collaborations not only help share the financial and intellectual load of these massive undertakings, but also drive the next era of discovery. Through these cooperative efforts, humanity is forging ahead into the vastness of space, uncovering the hidden worlds that lie beyond our view and deepening our understanding of the universe. Exoplanets are not just fascinating in their own right. They hold the potential to reveal crucial insights into the nature of planetary formation and the forces that govern the evolution of celestial bodies. For years, scientists formulated theories about planets based largely on our own solar system, anticipating that exoplanets would resemble the familiar Earth-like worlds or the giant gas planets that we know so well. However, the reality has proven to be far more complex and intriguing. As astronomers continue to uncover exoplanets of all shapes and sizes, the diversity of these worlds is forcing us to rethink our assumptions about what a planet should be. By comparing the properties of exoplanets with those of our own solar system, researchers are refining their understanding of how planets form and how they may be capable of supporting life. This interdisciplinary exploration brings together the fields of astronomy, planetary science, chemistry, climate science, and astrobiology, each contributing valuable insights that allow us to build a fuller picture of these distant worlds. Planetary science, for example, has provided critical knowledge about how planets form and evolve, helping to shape our understanding of exoplanetary atmospheres and surface conditions. Climate science has helped us simulate how weather patterns might work on distant planets, especially those in the habitable zone where liquid water could exist. These insights are vital for determining whether an exoplanet is capable of sustaining life. Meanwhile, astrobiology, by studying extreme life forms on Earth, explores the limits of life and helps identify the types of environments where life might thrive on other worlds. Together, these scientific fields are working in harmony to answer the ultimate question: could life exist on exoplanets? As we continue to unravel the mysteries of these distant worlds, we are learning not only how they form and evolve, but also whether they might one day harbor life. In the end, the search for exoplanets is not just about discovering new planets. It's about expanding our understanding of the universe and our place within it. However, the discovery of exoplanets has brought to light an astonishing range of planetary characteristics, sparking a revolution in our understanding of the universe. These distant worlds, which orbit stars far from our own solar system, display an incredible diversity in terms of size, composition, and orbital patterns. As astronomers peer deeper into the cosmos, they're confronting a fundamental question: what processes govern the formation of these planets, and how do they evolve over time? One of the most striking revelations has been the discovery of gas giants orbiting extraordinarily close to their parent stars, worlds now classified as hot Jupiters. These massive planets, resembling Jupiter in their size and gaseous composition, challenge the long-held belief that gas giants can only form in the cooler, more distant regions of a star system. Classical planetary formation models had suggested that gas giants should accumulate further out, away from the intense heat of a star. However, the existence of hot Jupiters forces scientists to reconsider how planets form and migrate, raising intriguing questions about the mechanisms at play in planetary systems across the galaxy. The presence of these extreme planets is more than just an anomaly. It serves as a crucial puzzle piece in the larger picture of planetary dynamics. By studying how such massive planets could form in such inhospitable environments, astronomers are refining their theories of planetary formation, pushing the boundaries of what we thought was possible. This shift in understanding not only deepens our knowledge of planetary systems, but also opens the door to discovering new, unknown processes that govern planetary creation in distant corners of the universe. Yet, the mysteries don't end there. The more we explore these exoplanets, the more we encounter phenomena that demand a deeper understanding of quantum mechanics. This branch of physics, which governs the behavior of matter and energy at the smallest scales, has proven to be a vital tool for studying planetary atmospheres and climates. The interaction of light with molecules in an exoplanet's atmosphere produces a unique spectral signature, a cosmic fingerprint that can reveal the planet's chemical composition. Analyzing these spectra provides invaluable insights not only into the planetary environment, but also into how quantum mechanics influences materials under varying temperature and pressure conditions. In this context, exoplanets are far from mere curiosities. They are essential to answering some of the most profound questions in science. As researchers observe more and more of these alien worlds, they are constantly refining their theories, uncovering new layers of understanding about how planetary systems form, evolve, and interact with their environments. In doing so, they are all expanding the boundaries of quantum theory, as the behavior of matter on these distant planets might differ in ways that challenge our existing models. The discovery of on an exoplanet would undoubtedly be one of the most profound revelations in human history, fundamentally reshaping our understanding of consciousness and intelligence. For millennia, we have viewed consciousness as a trait that evolved in response to the unique conditions on Earth. But if life exists elsewhere, if intelligent life exists, then we must reconsider what factors contribute to consciousness. Is it an extraordinary fluke of evolution, or is it a more common outcome in the universe, potentially arising under a wide range of conditions? This question could lead us to rethink the very nature of intelligence. Currently, we associate consciousness with complex organisms, those capable of abstract thought, self-awareness, and problem-solving. But what if simpler life forms, perhaps microbial organisms on distant worlds, possess rudimentary forms of consciousness? Could even the most basic forms of life, those that don't seem capable of higher-level cognition, display signs of awareness or responsiveness? This possibility invites us to reconsider what it means to be alive or aware. Perhaps the line between sentient and non-sentient life isn't as clear-cut as we once thought. If intelligent extraterrestrial life were to be discovered, it could lead to a radical rethinking of what intelligence is. Imagine an alien civilization with an entirely different concept of consciousness, shaped by environmental conditions that we can scarcely imagine. This would challenge our human-centric view of intelligence and force us to broaden our definitions. Rather than viewing consciousness as a pinnacle of evolution, we might begin to see it as a diverse set of tools, adapted to the specific challenges faced by different life forms across the universe. In this context, consciousness might not be a singular, universal phenomenon, but rather a vast spectrum of experiences and adaptations, each uniquely suited to the environment in which it developed. The philosophical implications of such discoveries would be profound. If intelligence is not a rare end result of evolution, but instead a varied and adaptive trait, then our place in the cosmos might seem less unique than we have imagined. We may find ourselves questioning not only what makes us human, but what it means to be alive, aware, and intelligent in the vast, unknown universe. The discovery of life, intelligent or otherwise, on exoplanets would challenge us to rethink our definitions of life itself, offering new perspectives on the interconnectedness of all living things, regardless of their origin. In exploring exoplanets, we are not just uncovering new worlds, but also uncovering the fundamental laws that govern the universe itself. The laws of physics, which apply universally, provide a foundation for understanding everything from gravitational pull to electromagnetic forces, shaping the way planets form, evolve, and interact with their stars. These universal principles are at work in the farthest reaches of space, determining the conditions for life or its absence on countless exoplanets. When astronomers discover exoplanets, they apply the same laws of physics that govern our own solar system to understand the properties of these distant worlds. Gravitational forces determine the orbits of planets around their stars, while the interactions of radiation from the star influence the temperature and atmospheric conditions on the planets. The boiling point of water, the strength of gravity, and the principles of thermodynamics all play a crucial role in determining whether an exoplanet might support life as we know it. For instance, if an exoplanet is too close to its star, the intense heat could prevent water from remaining in liquid form, making it inhospitable to life. Conversely, if a planet is located too far from its star, it might be too cold to support life, with conditions that are equally unwelcoming. These fundamental physical principles are not just abstract concepts. They shape the reality of distant worlds, offering a glimpse into the conditions that might support or hinder life across the galaxy. As we continue to explore exoplanets, we are not only gaining new insights into the workings of the universe, but we are also refining our understanding of the delicate balance that makes life possible. Each new discovery, each new exoplanet adds to the intricate puzzle of how life and consciousness emerges in the universe. And as our tools and techniques improve, we may be on the verge of answering questions that have intrigued humanity for centuries. Are we alone in the universe? What does it mean to be alive? And perhaps most profoundly, what is the true nature of consciousness itself? However, the conditions on exoplanets vary dramatically, giving rise to a captivating array of environments across the cosmos. Some exoplanets reside within what astronomers call the habitable zone, a region where the temperature is just right to allow liquid water to exist, a fundamental ingredient for life as we know it. Others, however, possess thick, dense atmospheres that trap heat through a potent greenhouse effect. These atmospheres may create conditions ripe for complex chemical reactions, potentially fostering unique forms of life or pre-life processes. Despite these differences, the laws of physics are universal, allowing scientists to predict certain behaviors of these distant worlds based on their environmental conditions. Whether it's the temperature fluctuations on a gas giant or the geological activity on an Earth-like rocky planet, these principles provide a lens through which we can interpret the vast variety of exoplanetary environments. As astronomers analyze data gathered from advanced telescopes and daring space missions, they rely on these immutable laws to decode the intricate details of these alien worlds. From determining the chemical makeup of alien atmospheres to unveiling the surface features of rocky planets, each new discovery brings us a little closer to understanding the diversity and complexity of the universe. The discovery of exoplanets, especially in systems with multiple planets, has given researchers the chance to study how these planets interact with each other. The gravitational dynamics between them offer critical insights into the processes that shape planetary systems, including our own. When we observe a collection of planets orbiting a single star, it suggests a different formation history than solitary planets. In multiplanetary systems, the planets exert gravitational forces on one another, altering their orbits in a kind of cosmic dance. This gravitational tug-of-war can lead to more stable or unstable orbital arrangements over time. The interactions between planets in such systems provide valuable clues about how planetary systems evolve and potentially how habitable zones may arise. For instance, when a planet's orbit is influenced by the gravitational pull of neighboring worlds, it may be pushed into or out of the habitable zone. The interplay of these planetary forces may, in turn, determine whether the conditions in a system are suitable for life. When astronomers observe these systems, they learn about the likelihood of various types of planets coexisting and the potential for environments where liquid water, and by extension, life, could exist. Single planet systems, in contrast, bring a different set of questions into focus. The absence of companion planets around a star invites speculation about why this is the case. Did the system form without the necessary ingredients for multiple planets, or did other planets form but later get ejected or destroyed? These solitary planets could have developed along a unique path, offering a different kind of insight into the processes that govern planetary formation. The discovery of more and more of these single-planet systems prompts ongoing discussions about the myriad environmental factors that influence the birth and evolution of worlds in our galaxy. By examining both multiplanetary and single-planet systems, scientists can piece together a more comprehensive understanding of planetary ecosystems. These studies enhance our models of how planets form and migrate through their host systems, improving our understanding of how life-sustaining planets may emerge. Each new discovery, whether it's of a solitary world or a bustling system of planets, brings us closer to unraveling the mysteries of our universe and identifying the cosmic neighborhoods where life might thrive. In systems with multiple planets, the gravitational interactions between them play a crucial role in shaping the future of the entire star system. When planets orbit a star, their gravitational pulls don't just affect their own paths, they influence the orbits of their neighboring planets, creating a complex web of gravitational forces. Over millions of years, this interconnected dance can lead to profound changes in the orbits of the planets, shifting their shapes and altering their distances from the star. For example, a massive planet like Jupiter, with its enormous mass, can pull on the orbits of smaller planets in the system. This can stabilize the orbits of some planets, making their paths more circular and predictable, while destabilizing others, potentially sending them hurtling out of the system or colliding with other objects. These gravitational forces also shape the fate of smaller celestial bodies, such as asteroids and comets. As these objects are pulled by the planets, they can be deflected, captured, or even ejected from the system. But the gravitational influence extends beyond just the planets. The interactions between the planets can also affect the host star, influencing its rotation and even its magnetic activity. These changes in the star's behavior, in turn, have a profound effect on the conditions in the habitable zone. Variations in the star's magnetic field or in its solar output can drastically alter the potential for life-supporting conditions on planets orbiting within that zone. In essence, the gravitational dynamics within a planetary system are essential not only for the stability of the planets, but for the evolution of the system as a whole. These interactions can foster the creation of habitable environments, or conversely, they may render conditions too unstable for life to take root. The interplay of gravitational forces thus becomes a fundamental factor in shaping the story of a star system, determining whether it will nurture life or remain a barren, lifeless expanse. Exoplanets, planets that orbit stars outside our solar system, showcase an astonishing range of orbital configurations, revealing much about their formation and the broader dynamics of their systems. One of the most striking characteristics observed is the variety in the shapes of their orbits. While Earth follows a nearly circular orbit around the Sun, many exoplanets follow highly elliptical paths. These elongated orbits bring the planets dramatically closer to their stars at certain points in their orbits, only to carry them far away at others. This variation suggests that the orbits of exoplanets are often influenced by gravitational interactions with other planets in the system, which can cause their trajectories to shift over time. Another intriguing feature of these orbits is their alignment relative to their host star. In some systems, the planet's orbits are aligned with the star's equatorial plane. This alignment could be a sign that the protoplanetary disk, the swirling cloud of gas and dust from which planets form, was stable and uniform during the planet's formation. A system like this might have experienced a relatively peaceful history, with the planets gradually coalescing from the same material in a way that produced harmonious orbits. As astronomers continue to uncover new exoplanets, they piece together an ever-evolving picture of how planetary systems form, interact, and evolve. These discoveries not only deepen our understanding of distant star systems, but also allow us to reflect on the origins and fate of our own solar system, prompting questions about the future of Earth and the potential for life elsewhere in the universe. The vastness of the universe is replete with mysteries, some of which have recently been illuminated through groundbreaking discoveries in the field of exoplanetary science. Astronomers have uncovered planetary systems where the orbits of planets are not just simple circles or ellipses, but are tilted at significant angles to their respective stellar planes. This revelation points to a tumultuous past for many of these systems, one that likely involved close encounters with other celestial bodies or complex migration patterns. These odd alignments and eccentric orbital shapes raise important questions about the true nature of planetary formation. What do these phenomena imply about the origins of these planetary systems? The answer, it seems, is that the processes of planetary formation are far more chaotic and unpredictable than once imagined. A planet's path around its star is influenced by numerous factors, including the mass of the star, the presence of other planets in the system, and even the gravitational pull of nearby stars. Each system, in turn, follows a unique evolutionary trajectory. For example, crowded planetary environments with large, massive planets often give rise to more eccentric or elongated orbits. These strange orbital patterns provide essential clues about the forces that shaped these planetary systems during their early formative years. The wide variety of orbital configurations and alignments observed in exoplanetary systems offers us a window into understanding not just the individual nature of these far-off worlds, but also the broader mechanics of astrophysics. By examining these variations, scientists are piecing together the story of how planetary systems come into being, evolve, and potentially develop the conditions that could support life. This journey is a critical part of planetary science, which has undergone a dramatic transformation over the past few decades. The tale of exoplanetary science began in the early 1990s when astronomers made the first confirmed discovery of an exoplanet, a planet orbiting a star outside our solar system. This historic breakthrough marked a pivotal moment in our understanding of the universe and opened the floodgates to a whole new realm of cosmic exploration. Since that time, as technology advanced, so too did our methods for detecting and studying distant worlds. In the early days, astronomers relied heavily on the radial velocity method, a technique that measures the gravitational influence of a planet on its host star. This method was crucial in confirming the presence of exoplanets, but it was soon supplemented by more advanced techniques. One of the most successful methods for detecting exoplanets is the transit technique. This approach involves detecting the faint dimming of a star's light as a planet passes in front of it, effectively blocking a small fraction of the light. Space telescopes like Kepler and more recently TESS, Transiting Exoplanet Survey Satellite, have significantly expanded our catalog of known exoplanets, increasing the number of confirmed exoplanets from a handful to thousands. What's more, our understanding of the types of exoplanets has expanded significantly. In the early days of exoplanet research, scientists focused mainly on large gas giants, planets like Jupiter and Saturn, believing these to be the most likely candidates for detection. Today, however, we recognize an astonishing diversity of planetary types, from hot Jupiters, gas giants that orbit extremely close to their stars, to rocky Earth-sized planets situated within the habitable zone of their stars. The variety of exoplanets challenges our initial assumptions. This diversity raises compelling questions about how planets form and evolve, and whether any of these distant worlds might harbor the conditions necessary for life. In addition to discovering new planets, the study of exoplanetary atmospheres has become a central focus of current research. By analyzing the starlight that passes through a planet's atmosphere during a transit, scientists can determine which gases are present. This analysis provides invaluable insights into a planet's climate, its potential habitability, and the processes that have shaped its atmosphere. As our understanding of exoplanets grows, so too does our ability to investigate the broader evolutionary pathways of planetary systems and the potential for life beyond our own planet. The history of exoplanetary science is deeply intertwined with the history of astronomy itself. Among the key figures who helped lay the groundwork for modern exoplanet research is the renowned Italian scientist Galileo Galilei. In the early 17th century, Galileo's pioneering observations, made using one of the first telescopes, fundamentally altered our understanding of the cosmos. His studies of celestial bodies in our solar system, including the moons of Jupiter, encouraged future generations to wonder about the existence of planets orbiting stars other than our Sun. Moving into the late 20th century, the field of exoplanetary research gained further momentum, thanks in part to the work of astrophysicist Frank Drake. In 1960, Drake developed the now famous Drake equation, which sought to estimate the number of communicative civilizations in our galaxy. Although the equation was primarily designed to guide the search for extraterrestrial life, it also underscored the importance of understanding other planetary systems, helping to spur increased interest and research into exoplanets. Another key milestone in the history of exoplanet discovery came in 1995, when Swiss astronomers Michel Mayor and Didier Queloz confirmed the existence of an exoplanet orbiting a Sun-like star. The planet, named 51 Pegasi b, was a gas giant with a highly elliptical orbit, and its discovery sent shockwaves through the scientific community. This breakthrough opened the door to thousands of other exoplanet discoveries, forever changing the trajectory of astronomical research. In addition to individual scientists, technological advancements have played an essential role in the development of exoplanetary science. The Hubble Space Telescope, launched in 1990, made significant contributions to the study of distant planetary systems. Yet perhaps the most transformative of all has been the Kepler Space Telescope, which launched in 2009. Kepler's mission was designed with a singular purpose: to discover new exoplanets by monitoring the brightness of over 150,000 stars. Through this mission, Kepler expanded our understanding of planetary systems and revolutionized our ability to detect planets. Despite these advances, the journey of exoplanetary science has not been without its challenges. Past scientific misconceptions have shaped the way contemporary researchers approach their studies. Early astronomers, constrained by the limited technology of their time, often made sweeping conclusions that have since been proven wrong. For example, many early thinkers believed that the planets moved in perfect circular orbits and that Earth was the center of the universe. These geocentric views prevailed for centuries until the observations of Copernicus, Kepler, and Galileo led to a paradigm shift toward a heliocentric model of the solar system. These historical missteps remind us of the importance of questioning established beliefs and being open to new evidence. The evolution from a geocentric to a heliocentric model represents a turning point in our understanding of the universe. It underscores the value of skepticism in science and serves as a cautionary tale for today's researchers. Modern planetary scientists design experiments and observations that rigorously test hypotheses, constantly striving to avoid repeating the errors of the past. In the end, the field of planetary science is defined by its continual transformation and expansion. The discoveries of today offer new opportunities for understanding the past, present, and future of the universe. As we continue to explore the stars and the countless worlds beyond our solar system, we find ourselves closer than ever to understanding not just the mechanics of planetary systems, but also the potential for life to exist beyond Earth. This ongoing journey of discovery reflects humanity's unyielding curiosity, pushing the boundaries of what we know and offering glimpses into the infinite possibilities of the cosmos. These misconceptions about our understanding of the universe have not only shaped the course of scientific inquiry, but also influenced technological advancements and the methodologies used in research. Take, for example, the realization that planets do not travel in perfect circular orbits, a discovery that forced a rethinking of long-held beliefs. This shift in understanding prompted the creation of more sophisticated models and the development of powerful simulation software. As a result, researchers today can explore the cosmos with a level of precision that was once unimaginable. Advanced algorithms and cutting-edge tools such as the James Webb Space Telescope allow scientists to peer deep into space, providing us with views and insights that previous generations could only dream of. With each correction of past misconceptions, our methods of exploration and research have become increasingly refined. For instance, scientists now account for factors such as atmospheric conditions and gravitational influences, variables that were once overlooked. The more we understand about the cosmos, the more we realize how much we still have yet to learn. This ongoing process of refinement is essential for advancing our knowledge of space, just as it is for advancing the methodologies used to explore it. Education plays an essential role in this narrative. Teaching future generations of scientists about how our understanding of the universe has evolved is just as important as the scientific principles themselves. By incorporating the history of misconceptions into curricula, we not only provide context, but also instill a deeper appreciation for the scientific method. Students learn that science is not a linear path to truth, but rather a journey of revisions, refinements, and adaptations. This helps foster an environment where curiosity and skepticism thrive, driving an ongoing quest for knowledge. Through this understanding, researchers are better equipped to avoid the pitfalls of oversimplified conclusions, ensuring that modern research methodologies are robust and resilient. By reflecting on our past missteps, we empower the future of exploration, both of the planets and beyond. One of the most exciting possibilities is the discovery of advanced civilizations on exoplanets. If such civilizations exist, it would carry profound implications for the future of humanity. One of the most intriguing aspects is the potential for collaboration. If we were to find civilizations that have mastered technologies far beyond our own, it could open the door to an exchange of knowledge. This could help us address some of the most pressing issues facing Earth today, including climate change, resource scarcity, and public health crises. The technological advancements of these civilizations might offer us the tools to solve problems that seem insurmountable at present, accelerating our own evolution in areas where we currently struggle. The existence of intelligent life elsewhere also invites us to reflect on our own trajectory as a species. By studying the rise and fall of other civilizations, we could gain valuable insights into the sustainability of societies over time. For instance, if we were to find evidence that advanced civilizations had survived for thousands or even millions of years, it might inspire us to consider how we could extend the lifespan of our own civilization. How could we balance technological growth with the preservation of the environment and societal stability? The histories of these civilizations could provide us with important lessons in resilience, cooperation, and ethical governance. However, the discovery of advanced civilizations also raises a note of caution. While the potential for cooperation is enticing, the risk of conflict or misunderstanding cannot be ignored. If such civilizations view us as primitive, or if we misinterpret their intentions, the consequences could be catastrophic. Furthermore, the idea that technological advancement inevitably leads to moral progress is not guaranteed. If we are to learn from the mistakes of other civilizations, we must also recognize that the ethical implications of technological growth are not always straightforward. Understanding these dynamics could have far-reaching implications for global discussions on technology, surveillance, and our collective responsibility as stewards of Earth. Ultimately, contemplating the existence of advanced civilizations forces us to turn inward. It challenges us to critically examine our values, behaviors, and priorities. This exploration could serve as a powerful reminder of the importance of global cooperation and unity, as we confront not just the challenges on our own planet, but also the vastness of the cosmos. Recognizing that we are not isolated in the universe could inspire a renewed sense of purpose, compelling us to become better custodians of the Earth and, perhaps, a more enlightened part of a broader cosmic community. One philosophical movement that is particularly relevant to the future of human civilization is transhumanism. This movement advocates for the enhancement of the human condition through advanced technologies, exploring the potential for humans to evolve beyond their current physical and mental limitations. In the context of exoplanet exploration, transhumanism raises important questions about humanity's long-term survival. As Earth faces escalating challenges, climate change, resource depletion, and potential existential threats like asteroid impacts, the idea of colonizing exoplanets becomes increasingly plausible. Transhumanists envision a future where humans are equipped with enhanced capabilities, such as improved physical traits, advanced cognitive functions, or even biotechnological adaptations that would make it possible to survive and thrive on distant worlds. These advancements could allow us to withstand the harsh conditions of alien environments, such as extreme temperatures, reduced gravity, or lack of breathable air. This futuristic perspective encourages the development of technologies that go beyond the limitations of our current biology. It suggests that in order to survive and thrive on exoplanets, humanity must not only adapt technologically, but also evolve biologically. The dream of creating human beings capable of flourishing in environments once thought inhospitable has become more than just science fiction. It is increasingly seen as a necessity for the future of our species. In this way, transhumanism offers a hopeful vision of humanity's future, one that is not limited by the constraints of our current physical and mental abilities. Instead, it imagines a world where we can overcome the challenges of space exploration, environmental degradation, and even the boundaries of human existence itself. Exploring exoplanets opens up a thrilling new frontier, where the possibilities of human evolution and space exploration converge. As we venture into the unknown, seeking new worlds that could harbor life, the very concept of humanity's future might need to be reimagined. If colonization of distant planets becomes essential, humans may be forced to reconsider what it truly means to be human. In this context, transhumanism emerges as a powerful idea, suggesting that human biology should be merged with advanced technologies to overcome the limitations that Earth-bound bodies face. Transhumanists propose creating hybrid beings, combining human biology with artificial intelligence, or enhancing our natural abilities through genetic engineering. These innovations could enable us to survive and thrive in environments that are inhospitable to present-day humans. In the pursuit of exoplanets, transhumanism becomes more than an ideal. It could be a crucial step in ensuring humanity's survival. As we expand our horizons and look to the stars, it is clear that enhancing human capabilities will be essential. By merging technology with our biological essence, we may not only discover new homes beyond Earth, but also redefine the very concept of what it means to be human in a universe filled with boundless possibilities. The journey into the vastness of the cosmos sparks imagination and fuels our desire to explore distant exoplanets. The prospect of studying these remote worlds is more exciting than ever as emerging technologies make the impossible possible. One of the most groundbreaking innovations in this field is the advent of advanced space telescopes, such as the James Webb Space Telescope. Designed to peer further into the universe than any telescope before it, the James Webb Space Telescope has the capability to detect the faintest signals from faraway planets. It analyzes light passing through a planet's atmosphere, uncovering chemical signatures that could indicate the presence of essential elements like water, methane, and oxygen, key ingredients for potential life. Robotic space missions represent another exhilarating development in exoplanet exploration. Concepts like the Interstellar Probe aim to journey beyond our solar system, gathering data from neighboring star systems. These probes could utilize cutting-edge propulsion technologies, such as solar sails or ion drives, allowing them to cover vast distances at unprecedented speeds. By sending these robotic explorers equipped with advanced instruments, we could gain unprecedented insights into the surface and atmospheric conditions of exoplanets, providing crucial information about their habitability. Artificial intelligence, AI, is also playing a pivotal role in this unfolding narrative. AI systems can process vast amounts of astronomical data far faster than human researchers ever could. Machine learning algorithms allow scientists to identify patterns and anomalies in light curves, which may suggest the presence of exoplanets or even signs of biological activity. This ability accelerates the discovery process and provides fresh perspectives on exoplanets that have already been identified, potentially revealing new aspects of their environments that were previously overlooked. Another exciting prospect in space exploration is the concept of space elevators, which could revolutionize access to space. A space elevator would consist of a cable tethered to a base on Earth, stretching into the heavens. Such a structure could dramatically lower the cost of reaching orbit, making it easier to deploy sophisticated instruments designed to study exoplanets. While still a theoretical concept, the idea of a space elevator could make space travel more efficient and economically viable, potentially transforming how we launch missions to distant stars. As these technologies continue to develop, the dream of understanding exoplanets grows closer to reality. What once seemed like science fiction is now becoming increasingly plausible. The process of educating the public about exoplanets is an essential part of this journey. Captivating storytelling is one of the most effective ways to engage people with this fascinating subject. When scientists present their discoveries about distant worlds in the form of compelling narratives, it brings complex data to life, helping audiences connect with the science on a deeper emotional level. By framing the search for exoplanets as the journey of a planet similar to Earth, the story becomes more than just a scientific endeavor. It becomes an inspiring quest for understanding and exploration. Interactive platforms such as science centers and planetariums also play a vital role in this educational process. By offering immersive experiences like virtual and augmented reality, these institutions allow people to virtually travel to distant exoplanets and experience the conditions of these remote worlds firsthand. These technologies turn abstract concepts into something tangible, sparking a sense of awe and wonder that is essential for fostering a lifelong interest in space exploration. They don't just inform, they inspire. Social media has become a powerful tool for generating excitement about exoplanets and their potential for human habitation. Platforms like Twitter, Instagram, and Facebook allow scientists to share real-time updates, stunning visuals, and engaging infographics that captivate global audiences. This instant access to groundbreaking discoveries helps to bridge the gap between scientific communities and the general public. Social media's ability to share breathtaking images of distant worlds alongside engaging stories makes complex scientific data more accessible, democratizing the information and making it relatable to a wider audience. One of the most effective ways to harness social media is through the use of compelling imagery and interactive content. Pictures of exoplanets captured by telescopes can be paired with infographics that explain their significance. Virtual simulations of exoplanets and real-time discussions on platforms like Twitter can create a dynamic dialogue, engaging people in ways that traditional scientific publications cannot. By collaborating with influencers and science communicators, scientists can reach even broader audiences, helping to spark public interest and curiosity about the mysteries of the universe. Special events, such as significant discoveries or anniversaries of landmark missions, provide an excellent opportunity to generate collective excitement. Hashtags, live streams, and countdowns can engage audiences and create a sense of community, transforming a scientific milestone into a shared journey of exploration. Social media has the power to turn distant celestial discoveries into an interactive experience, keeping the conversation alive and encouraging further participation. It can inspire enthusiasm for astronomy and help people develop a deeper understanding of our place in the cosmos. Educational institutions play a crucial role in nurturing the next generation of astronomers, astrophysicists, and exoplanet researchers. By providing the foundational knowledge and skills needed to explore the vastness of space, schools and universities foster curiosity and inspire students to pursue careers in science and technology. Through structured learning environments, students are introduced to subjects like physics, mathematics, and computer science, essential tools for understanding celestial bodies and the complexities of space exploration. By integrating exoplanet science and space exploration into the curriculum, educators can spark a sense of wonder in the next generation, creating a workforce dedicated to uncovering the mysteries of the universe. In this age of rapid technological advancements and collaborative global efforts, the quest to understand exoplanets becomes more than just an academic pursuit. It is a mission that connects humanity to the stars, encouraging us to expand our horizons and reconsider what is possible. As we look to the future, the intersection of transhumanism, space exploration, and exoplanet research promises to reshape both our understanding of the cosmos and our very identity as a species. The stars are calling, and it is up to us to answer. Educational institutions have long been at the forefront of scientific discovery, particularly in fields as vast and complex as astronomy. Universities, research centers, and observatories serve as the essential hubs where knowledge and curiosity converge, creating an environment conducive to groundbreaking research. These institutions are not just places for theoretical learning, but active centers for experimentation, exploration, and innovation. Many universities host sophisticated observatories and specialized research facilities, offering students and faculty hands-on opportunities to engage directly with the mysteries of the universe. It is in these environments that practical skills are cultivated, from mastering the intricate operation of telescopes to analyzing complex data sets. Students gain invaluable experience that extends far beyond textbooks, learning research methodologies that are crucial for the next generation of discoveries. The collaborative nature of these institutions fosters an atmosphere where new ideas can thrive. Students, professors, and researchers work side by side, often in cross-disciplinary teams, to explore unexplored corners of the cosmos. This collaboration frequently results in groundbreaking discoveries, enriching our understanding of exoplanets, black holes, and other celestial phenomena. It is not merely a place for isolated study, but a dynamic space where diverse minds come together to push the boundaries of what we know. In this environment, mentorship plays an irreplaceable role. Professors and senior researchers provide guidance that goes beyond academic instruction, offering students the wisdom and support needed to navigate complex academic pathways, develop their research skills, and ultimately pursue successful careers in space exploration and beyond. Networking within these institutions often leads to fruitful collaborations between budding scientists and professionals already established in the field. These connections not only amplify the students' learning experiences, but also open doors to future career opportunities. By fostering this spirit of collaboration, educational institutions lay the groundwork for the next wave of astronomers, engineers, and researchers who will shape the future of space science. Moreover, educational institutions are integral in making the wonders of the cosmos accessible to a broader public. Through outreach programs, public lectures, and hands-on workshops, universities engage with the community, sparking curiosity and educating the public about the importance of space exploration and scientific discovery. These initiatives help demystify the universe and encourage the next generation of scientists, engineers, and explorers to think critically about the world around them. By introducing young people to the limitless possibilities of space, these institutions are not only shaping the workforce of tomorrow, but cultivating a culture of scientific curiosity and awe that will inspire future generations. The study of exoplanets, planets orbiting stars beyond our solar system, has profoundly transformed our understanding of where life might exist beyond Earth. For centuries, scientists speculated that Earth was unique in its ability to support life, but the discovery of exoplanets has opened up a whole new realm of possibility. Initially, astronomers focused on identifying planets that shared characteristics with Earth, with the hope that they might offer the right conditions to host life. However, as technology has advanced, scientists have discovered thousands of these distant worlds, revealing an astonishing diversity in their characteristics and environments. This ever-expanding catalog of exoplanets has forced scientists to rethink what conditions are necessary for life to thrive. Many of these exoplanets orbit within what is known as the habitable zone of their parent stars, the region where temperatures are conducive to the existence of liquid water, the key ingredient for life as we understand it. However, the search for life shouldn't be limited to Earth-like planets in this habitable zone. The discovery of extremophiles, organisms that thrive in Earth's most inhospitable environments, has opened scientists' eyes to the possibility that life could exist in places previously thought to be too extreme for survival. This insight has expanded the scope of the search for life, leading scientists to consider alternative environments, such as the cold, gaseous giants or icy moons in our own solar system, where subsurface oceans might harbor microbial life. The methods used to study exoplanets have also evolved, providing a wealth of new insights into the potential for life beyond Earth. By observing the light filtering through an exoplanet's atmosphere as it passes in front of its star, scientists can detect chemical compounds like oxygen or methane, gases that on Earth are closely linked to biological processes. The presence of such gases in the atmosphere of a distant exoplanet could be a strong indicator of life, offering tantalizing possibilities for identifying signs of life beyond our planet. These groundbreaking methods not only provide clues about the potential for life elsewhere, but also invite us to reflect on the unique nature of our own existence in the vast expanse of the universe. The exploration of exoplanets raises profound questions about our place in the cosmos. As we peer deeper into space, the growing realization that life might be more common than previously thought brings with it both awe and wonder. The search for exoplanets reignites one of humanity's oldest questions. Are we alone in the universe, or is life waiting to be discovered on distant worlds? The answers to these questions lie among the stars, beckoning us to continue exploring and seeking new knowledge. Each discovery made in the pursuit of understanding exoplanets not only adds to our knowledge of distant worlds, but also reaffirms our drive to explore the vastness of space. The discovery of exoplanets has also led to new methods of comparative analysis. By studying the chemical compositions of these distant worlds, scientists can infer a wealth of information about their atmospheres, geology, and the potential for life. Each exoplanet is unique, and by comparing their properties, such as temperature, pressure, and chemical makeup, astronomers can learn about the forces that shape these worlds. For example, an exoplanet that orbits close to its star might experience extreme heat, creating conditions that differ vastly from those on a cooler, more distant planet. By analyzing these differences, scientists gain insights into how chemical compounds form in varying environments and how they affect the planet's atmosphere, cloud formation, and potential for hosting life. The study of volatile elements such as water vapor, carbon dioxide, and methane can offer clues about the geological history of an exoplanet. The presence of certain gases like methane could indicate volcanic activity, suggesting that the planet has undergone significant geological processes. Conversely, the absence of expected compounds might suggest that a planet's environment is too harsh for complex chemical reactions to take place, steering the search for life toward more promising candidates. This kind of research is not just a theoretical exercise, it's a crucial piece of the puzzle in understanding planetary formation and evolution. Every piece of data gathered adds depth to our understanding of how these distant worlds came to be, and what conditions are necessary for life to emerge. The study of exoplanets has also proven to be an unexpected avenue for investigating dark matter, a mysterious substance that makes up a large portion of the universe's mass, but has yet to be directly observed. By studying how exoplanets interact with their stars, particularly their gravitational effects, astronomers can gather data that might provide insights into the distribution of dark matter. For example, when an exoplanet transits its star, causing a slight dimming in the star's light, researchers can analyze the light curve to infer the planet's size, mass, and orbit. This information, in turn, can help astronomers refine their models of how galaxies and other cosmic structures form, shedding light on the hidden mass of dark matter that influences the cosmos. By studying the movements and gravitational pull of these distant worlds, scientists are uncovering more about the unseen forces that shape our universe. In the end, the exploration of exoplanets offers not only a chance to understand alien worlds, but also a profound opportunity to better grasp the very forces that govern the universe. Through careful study and comparison, scientists are unraveling the mysteries of planetary formation, atmospheric chemistry, and the potential for life beyond Earth. And in doing so, they are not just expanding our knowledge of distant stars, they are pushing the boundaries of human discovery, exploring the depths of space, and ultimately answering some of the most profound questions about our existence. Peculiarities in the motion of exoplanets could, in fact, serve as potential fingerprints of dark matter, provided that dark matter exists in clumps scattered throughout the universe. If dark matter is indeed distributed in this way, these clumps could exert subtle gravitational forces that influence the orbits of nearby celestial bodies, including exoplanets. Such gravitational interactions, though faint, are detectable. By observing how these exoplanets move in relation to their parent stars and the gravitational disturbances they experience, astronomers could infer the presence of dark matter, piecing together its distribution and density across the cosmos. This method of detection presents a fascinating opportunity. Not only does it allow us to study exoplanets, but it also deepens our understanding of the elusive dark matter that is believed to shape the entire structure of the universe. As technology advances, particularly with more sophisticated telescopes and detection techniques, we are able to observe more exoplanets and refine our knowledge of both these distant worlds and the shadowy presence of dark matter. Each new discovery adds another layer to the grand cosmic puzzle, drawing us closer to answering the most profound questions we have about the very fabric of reality. But beyond the scientific pursuit of understanding dark matter, the detection of exoplanets introduces profound existential questions. Among the most pressing is the question of life beyond Earth. Are we alone in the vastness of the universe, or is there a rich diversity of life forms scattered across distant stars? The discovery of extraterrestrial life would not only answer that question, but it would also fundamentally alter our perception of life itself. What does it mean to be human in a universe where life exists elsewhere? The discovery of life on exoplanets raises another critical inquiry. What is the nature of intelligence? If life does exist on other worlds, how similar or different might those beings be to us? Would they possess consciousness, culture, or even technology? These questions force us to consider the possibility of diverse forms of life, each with their own unique experiences and ways of perceiving reality. This would inevitably prompt a re-evaluation of our assumptions about communication, understanding, and even relationships with potentially very different forms of intelligence. In a broader sense, the discovery of life elsewhere could have serious implications for our own existence and survival. It would invite us to ask whether life on Earth is a rare phenomenon or simply one example of countless life forms thriving across the universe. This question extends into the realm of survival itself. Could life, in its various forms, thrive in environments that are extreme by Earth standards? The study of exoplanets' inhabitable zones could offer insights into the resilience and adaptability of life, expanding our understanding of the potential for survival in the most inhospitable conditions. Furthermore, the discovery of intelligent life on exoplanets would spark profound philosophical debates on ethics and responsibility. How should humanity approach such a discovery? If we were to make contact, what would that relationship look like? The realization that we share the universe with other sentient beings places humanity in a much larger ethical framework, one that transcends Earth itself. It challenges us to consider how we relate to other life forms, how we interact with our own planet, and how we assume responsibility as stewards of all life in the cosmos. In the realm of science, philosophical perspectives play an essential role in how we interpret our findings about exoplanets. At the heart of scientific inquiry lies the fundamental question: what is the nature of reality? This question, when examined through different philosophical lenses, can dramatically alter the way we approach the data gathered from telescopes, space probes, and other research methods. For example, a materialist viewpoint might focus strictly on the physical, measurable aspects of exoplanets, often sidelining any abstract or speculative implications. On the other hand, an idealist perspective might inspire scientists to explore the possibility of life or consciousness beyond Earth, which could shift the focus of research from merely identifying planets to investigating the conditions for life or even the potential for advanced civilizations. Another crucial philosophical element that shapes our understanding is epistemology, the study of knowledge itself. Epistemology guides scientists in interpreting the evidence they collect. Those with an empirical mindset might emphasize direct, observable data and reproducibility as the foundations of scientific progress. In contrast, others might argue that broader theoretical frameworks influenced by philosophical concepts are necessary to interpret the more sparse or indirect evidence that we often encounter in exoplanet research. Methods such as the transit technique or spectrographic analysis provide valuable but sometimes incomplete information, necessitating an interpretive framework shaped by philosophical thought. This interplay between philosophy and science fosters deeper inquiry into the nature of exoplanets and their significance. As we probe the mysteries of these distant worlds, we are forced to confront assumptions about life, existence, and our own place in the universe. These philosophical perspectives are not mere abstractions. They directly influence the questions we ask, the ways we conceptualize the cosmos, and the importance we assign to our discoveries. With each new study of exoplanets, we are inching closer to a broader understanding of the universe, one that marries the empirical rigor of scientific exploration with the rich complexity of philosophical thought. The discovery of exoplanets, those planets orbiting stars outside our solar system, has revolutionized our perception of the cosmos. For much of history, our view of the universe was shaped by anthropocentrism, the belief that human beings are the central or most significant entities in the grand scheme of existence. Earth was seen as the pinnacle of creation, a unique bastion of life. But the discovery of thousands of exoplanets, many of them potentially habitable, forces us to rethink this assumption. Perhaps we are not at the center of the universe after all. Rather, we are part of a far more complex and dynamic cosmic system, where countless worlds, some of them potentially harboring life, exist beyond our immediate understanding. Each new exoplanet discovery challenges the notion of Earth's uniqueness and nudges humanity toward a more humble and expansive view of its place in the grand cosmic tapestry. However, as we delve deeper into the discovery of thousands of exoplanets, many of which orbit within habitable zones, we began to uncover a profound truth. Earth is but one of countless worlds, possibly teeming with life and diverse ecosystems. This realization began to shift our perspective on the cosmos, prompting us to reassess our place and significance in the grand scale of the universe. The sheer variety of environments found on these distant planets is mind-boggling. Some worlds are eerily similar to Earth, while others display extreme, even inhospitable conditions. This diversity challenges our preconceived notion that life must necessarily resemble what we know. Instead, the potential for life to manifest in forms and ecosystems we have yet to imagine calls for a deeper humility in our assumptions, urging us to recognize the limits of our understanding. Rather than seeing ourselves as the center of the universe, humans may turn out to be just one possible outcome of a vast array of cosmic processes. Furthermore, this perspective invites reflection on anthropocentrism, the belief that human beings are the most significant entities in the universe. It intertwines with ethical considerations surrounding our treatment of the Earth and all its living inhabitants. If we accept that life may emerge in many forms across the cosmos, this recognition encourages us to respect and protect the diversity of life here on Earth. The realization that life may not be solely dependent on human civilization invites deeper questions about our role as stewards of this planet. As we continue our quest to discover new exoplanets, each new world stands as a reminder of the enormity of the cosmos, brimming with possibilities we have yet to comprehend. These distant planets urge us to expand the boundaries of our imagination, to consider life beyond the confines of our own limited experience. This expansion of thought fosters a sense of connection to the larger universe, shifting our viewpoint from one of dominance to one of shared existence. Such a shift calls for a richer, more inclusive relationship with the cosmos, a perspective that values all forms of life, not just those that mirror our own. In embracing this, we open ourselves to a more profound understanding of the universe, a place that holds mysteries far beyond our current reach. Throughout history, the concept of life beyond Earth has been interpreted in myriad ways, shaped by culture, belief, and scientific understanding. In many ancient societies, the stars were not mere points of light in the sky, but the dwelling places of divine beings or ancestors, influencing how they viewed the cosmos. For instance, in numerous indigenous cultures, celestial bodies were often deeply intertwined with creation myths, with life beyond Earth forming an integral part of their spiritual framework. These beliefs fostered a sense of connection to the universe, provoking questions about humanity's role in a much larger cosmic drama. On the other hand, during the Enlightenment, many Western cultures began to adopt a more scientific approach to the cosmos. The notion of extraterrestrial life shifted from myth and speculation to empirical inquiry, grounded in observation and reason. The works of philosophers and scientists such as Giordano Bruno and Carl Sagan paved the way for a broader public understanding of the universe as a vast expanse that could potentially harbor life. This shift sparked not only scientific curiosity, but also technological advancements, leading to space missions designed to find evidence of life beyond our own planet. Cultural beliefs have had a profound impact on how scientific exploration is shaped. For example, societies that view Earth as a unique entity may prioritize efforts to find life within our solar system, perhaps focusing on Mars or the moons of Jupiter and Saturn. In contrast, cultures that embrace the possibility of life elsewhere in the universe may broaden their search to include exoplanets in distant star systems. These differing cultural attitudes not only influence the funding and direction of research, but also shape public interest in space exploration. A culture's collective perspective on the universe ultimately informs how scientific inquiry is conducted and how we understand the nature of life itself. As diverse cultures continue to share their views on life in the cosmos, they enrich the scientific discourse and broaden our collective imagination. The intersection of cultural narratives and scientific inquiry enhances our understanding of the universe and the possibility of other life forms among the stars. This ongoing dialogue between humanity's diverse belief systems and the rigorous methods of scientific exploration keeps our curiosity alive, inviting each generation to reflect on the age-old question, what does it mean to be human in a universe that may not be as empty as we once thought? The global effort to study exoplanets has also demonstrated the power of international cooperation. By pooling resources, knowledge, and expertise, countries around the world can embark on more ambitious projects that would be impossible for any single nation to undertake. Such collaboration not only helps share the financial burden of space exploration, but also grants researchers access to cutting-edge technologies and advanced instrumentation, further enhancing our ability to detect and analyze distant worlds. Moreover, cross-border collaboration fosters a rich diversity of ideas and approaches. A satellite developed in one country may complement ground-based telescopes in another, enabling scientists to observe exoplanets from multiple angles and gather more comprehensive data. This kind of teamwork accelerates progress and enriches the scientific dialogue, creating an environment where researchers learn from one another's experiences and methodologies. Together, these international efforts have opened doors to a wealth of discoveries, expanding our understanding of the universe and the countless possibilities that lie beyond the stars. In the realm of astronomical discovery, the shared pursuit of understanding exoplanets, the distant worlds orbiting stars beyond our solar system, offers not just new knowledge, but an unparalleled opportunity for international collaboration. By pooling data from across the globe, scientists create a more thorough and comprehensive understanding of these celestial bodies. This united effort, where researchers from diverse countries contribute to a common database, amplifies the possibility of significant breakthroughs. The collective analysis of these exoplanets increases the chances of finding patterns and anomalies that may have otherwise gone unnoticed. Such cooperation doesn't just elevate the quality of research, it fosters a deeper, more inclusive exploration of the cosmos. The integration of diverse perspectives and methodologies leads to a richer, more nuanced understanding of potential planetary habitability, how the conditions on these distant planets could support life. This cross-cultural collaboration also enhances our comprehension of the myriad factors that shape a planet's atmosphere, its geological features, and the underlying conditions that determine whether a world is capable of sustaining life or whether it is inhospitable, like the harsh extremes found on some planets. Furthermore, the global collaboration involved in exoplanet exploration extends far beyond the realm of science. It has the potential to spark public interest in space and science, encouraging greater investment in research and development. Joint missions and projects across borders send a powerful message of unity and shared purpose. The idea that countries can work together to unlock the mysteries of the universe captures the public imagination. It highlights the very best of human potential, inspiring not only scientific curiosity, but also public engagement with the pursuit of knowledge. When researchers from various nations present their findings together, it demonstrates a collective human effort, a shared journey to understand the vast universe. This sense of shared purpose transcends national borders and unites us in the exploration of the cosmos, offering a profound reminder of what humanity can accomplish when it works together for the greater good. The study of exoplanets, therefore, is not just an exploration of distant stars, but also a testament to the power of collaboration. It speaks to the spirit of cooperation that has driven our species to look beyond the confines of our home planet. Exoplanets, by their very nature, represent the unknown. These distant worlds, orbiting stars beyond our solar system, hold the key to understanding the fundamental dynamics of planetary bodies, including Earth itself. By examining the atmospheres, geological features, and potential climates of these planets, scientists gain critical insights into the processes that shape not only distant worlds, but also our own. Such a comparative approach enables a more profound understanding of the Earth's own unique characteristics, shedding light on the challenges we face today. One of the most important lessons drawn from the study of exoplanets is the impact of extreme climate phenomena on planetary habitability. Some exoplanets with thick atmospheres that trap heat experience runaway greenhouse effects, creating conditions that are inhospitable to life as we know it. By studying these planets, scientists can gain a clearer perspective on Earth's delicate balance. It helps us better understand the importance of maintaining a stable atmosphere and the potential consequences of unchecked greenhouse gas emissions. As humanity grapples with climate change, these findings offer vital lessons on the long-term impacts of altering a planet's atmosphere. Furthermore, the study of geological activities on other planets, whether volcanic eruptions, tectonic shifts, or unique surface formations, provides a broader context for understanding Earth's own geological processes. Many exoplanets feature volcanic activity or tectonic features that serve as analogs to Earth's own geological features. By studying these worlds, researchers can refine their understanding of plate tectonics, the formation of mountains, and the ongoing evolution of planetary surfaces. This comparative approach enriches our understanding of Earth's natural disasters, such as earthquakes and volcanic eruptions, while helping scientists understand the larger forces that shape all planetary bodies. The search for life beyond Earth is another key driver in exoplanet research. Understanding the conditions that might foster life is essential for identifying which exoplanets could potentially support living organisms. By investigating planets located in the Goldilocks zone, where conditions are just right for liquid water, researchers can enhance their understanding of the factors that make Earth unique in the universe. This quest for habitable worlds is not just about finding life elsewhere. It offers insights into how we might preserve our own planet's delicate ecosystems in the face of growing environmental challenges. As we venture further into the study of exoplanets, several exciting themes are emerging that could reshape our understanding of the cosmos. One of the central themes is the search for potentially habitable worlds. Scientists are no longer simply cataloging newly discovered planets. They are actively analyzing their atmospheres and chemical compositions to determine if they might harbor the conditions necessary for life. Advanced instruments like the James Webb Space Telescope will play a crucial role in this research, enabling the analysis of exoplanet atmospheres for signs of vital indicators such as water vapor, methane, and other elements that could suggest the presence of life. Another significant theme in exoplanet research is the diversity of planetary systems. Our solar system, with its relatively uniform arrangement of rocky and gas planets, is just one of many possible configurations. Astronomers have discovered systems that challenge traditional models, featuring gas giants orbiting close to their stars, or even more exotic worlds like super-Earths and mini-Neptunes. Each new discovery broadens our understanding of the variety of planetary systems in the universe, prompting scientists to rethink the dynamics of planetary formation and migration. These revelations force us to question our assumptions about how planets form, evolve, and move through space. As technology continues to advance, so too does the potential to study exoplanet atmospheres in unprecedented detail. Future missions aim to identify chemical biosignatures, indicators that life as we know it might exist or have existed on these distant worlds. The ability to detect complex organic molecules or to analyze the light spectra from far-off planets will provide new insights into evolutionary processes and the potential for alternative forms of life that may exist in environments radically different from Earth's. But beyond the scientific and technological advancements, the exploration of exoplanets forces us to confront deeper philosophical questions about our place in the universe. The discovery of life elsewhere could profoundly alter our understanding of what it means to be human. It would expand our definitions of habitability and intelligence, forcing us to reevaluate what we consider life and how we might recognize it. Each exoplanet discovery not only adds a new chapter to our scientific knowledge, but also encourages us to reflect on our shared existence in the cosmos. As we continue to uncover the mysteries of distant worlds, the exploration of exoplanets offers a unique opportunity to deepen our connection to the universe. The study of these far-off planets invites us to consider both our own fragility and our potential, pushing the boundaries of our imagination and scientific capabilities. In the end, the study of exoplanets reminds us that we are part of something much larger than ourselves. Our journey to understand these distant worlds is not only about exploring the universe, it is a powerful reminder of the vast unknowns that still await discovery and the potential for awe and wonder that lies beyond our home planet. Documentaries are an essential medium in conveying the complexities of exoplanet research to the public. By combining breathtaking visuals with compelling narratives, documentaries can bring the wonders of exoplanet exploration to life. This visual storytelling allows audiences to envision the distant worlds that scientists are studying, how they are discovered, what their atmospheres might be like, and the many factors that make them unique. When viewers can visualize these distant planets and contemplate their potential for habitability, it sparks a sense of wonder and excitement about the universe, one that could inspire the next generation of scientists, explorers, and dreamers. Documentaries hold a unique power to make the incredibly complex world of exoplanets accessible and engaging. Through expert interviews and clear, approachable explanations, they break down the daunting mysteries of astrophysics and planetary science into understandable concepts. Scientists and astronomers, usually speaking in highly technical terms, are given a platform to distill these ideas into language that speaks directly to the public. For example, by explaining the transit method or radial velocity, filmmakers can show how these methods are used to detect exoplanets and study their features. These technical processes, which might otherwise seem impenetrable, are transformed into relatable concepts that viewers can grasp with ease. This method of simplification not only informs the audience, but also showcases the deep collaborative nature of scientific discovery. The enthusiasm and passion of researchers for their work come across clearly, making it evident that the search for exoplanets is not just about science, but about a shared human endeavor. Scientists, often working across continents, united by their desire to answer some of the most profound questions about our universe, become more than just figures of authority. They become part of a larger story, one that invites the audience into the world of scientific discovery. Through the lens of a documentary, viewers are not just passive recipients of information, but active participants in the journey of exploration. Their curiosity, sparked by the filmmakers' ability to convey the excitement and wonder that drives this work. The pacing of a documentary allows for a deeper, more thoughtful exploration of the themes that surround exoplanets. Unlike the rapid-fire nature of news segments or the brevity of typical educational content, documentaries offer the time and space to reflect on larger questions about life in the universe. As filmmakers weave together the story of new discoveries with the historical milestones that have shaped our understanding of planets, they guide audiences through a narrative that's not just about the present, but about the evolution of human curiosity. This approach invites viewers to think about the journey we have taken, from ancient stargazers gazing up at the night sky to modern scientists peering through telescopes and unraveling the mysteries of distant worlds. Through this storytelling, documentaries emphasize our role as explorers of the cosmos, reminding us that the search for knowledge is both a personal and collective mission. At the heart of this storytelling is the emotional resonance that documentaries are able to evoke. By focusing on the quest to find exoplanets, particularly those that may hold conditions similar to Earth, filmmakers tap into universal feelings of wonder, hope, and curiosity. The emotional engagement that follows is critical. It encourages viewers to not only appreciate the science itself, but to consider its broader implications for humanity. The search for planets beyond our own solar system is not just a scientific pursuit. It is a quest that speaks to our deepest questions about existence, our place in the universe, and the possibility of life elsewhere. Documentaries elevate this search, making it something that feels deeply personal, as though the journey is one that we are all taking together, regardless of where we live or what we do. In this way, documentaries can stimulate public interest in astronomy and science, fostering a greater sense of shared curiosity. They offer viewers the chance to see the world through the eyes of those pushing the boundaries of human knowledge, and they remind us all of the importance of continued scientific inquiry. Whether we're learning about distant exoplanets or the technologies that help us study them, these films encourage us to think critically about our role in the universe and the responsibility we bear to protect and explore it. With the power to inspire wonder, deepen understanding, and cultivate a sense of shared purpose, documentaries can leave a lasting impact, sparking a broader appreciation for the cosmos and the ongoing quest to unlock its secrets.